Okay. So yeah, so I'm gonna talk about altermagnets explored with core level spectroscopies, XMCD in particular, and let me acknowledge the collaborators. There are many people that contributed to this talk, but let me name in particular Atsushi Hariki, who did most of the calculations I'm gonna show you. So let me start by slides that you've probably seen many times before, and this is an introduction what an altermagnet is. So if you think about collinear magnets in real space, you can classify them or divide them in basically in two groups: magnets that have some non-zero net magnetization and magnets that have zero net magnetization. But if you look at the magnets in the reciprocal space, the classification gets richer. You can think about magnets where there is no magnetization in reciprocal space. We can call it no wave. Then ferro and ferrimagnets would be S wave, meaning that the net magnetization is finite. And then you have all the other partial waves, and these would be magnets that are nowadays called altermagnets. Well, of course, altermagnets, like any other broken symmetry phases, are primarily characterized by the symmetry. So the K-space classification is not the only one, but basically an altermagnet is a magnet where the order parameter, which is the field of magnetic moments on the lattice, transforms in a non-trivial way. So it's not an invariant under point group symmetries. And this fact is not new. Actually, many materials that we are studying nowadays have been known already in 60s and were thoroughly explored. It was also realized that they have some special properties, but probably, as Neil said in his Nobel lecture, that antiferromagnetic interesting but useless. Also, the utility of altermagnets were not realized at the time, and nowadays, with the advent of spintronics, their utility really came into forefront. So, one of the simple ways to characterize altermagnets is to say that these are compensated magnets where the time reverse states, so the states which are connected by flipping the moments, are macroscopically distinguishable. In symmetry terms, it means that the two magnetic sublattices are connected by symmetry operation, which contains rotation in some form. For my talk, I will use a bit a narrower property or definition of altermagnets. These are compensated, usually not fully compensated, collinear magnets, which allow linear magneto-optical effects. I say allow because there are symmetries or situations where the magneto-optical effects are not allowed. But in contrast to antiferromagnets, where the linear magneto-optical effects are always forbidden by time reverse symmetry. So this is the outline of my talk. I will start with the introduction of X-ray magnetic circle dichroism and its observation in manganese telluride. Then I will talk a little bit about the theory and symmetry considerations, and then I will show you results on difluorides, hematite, and bismuth ferrite, and mention some interesting symmetry aspects. And I will skip RIC-CD, which I announced in my abstract, because I realized that it would be too messy and too much. So if you are interested, you can ask, but I will probably not get into it. So X-ray magnetic circle dichroism is an old technique which has been very well established in studying ferromagnets, and it's conceptually very simple. You shine circularly polarized X-rays on your material, you measure absorption, and you look at the difference of the two absorption spectra. Theoretically, it's also quite simple, at least in dipole approximation. You have the Fermi golden rule, you have a ground state, you have a dipole matrix element, and you sum over all the final states. Now, there is a simplification when you look at X-ray absorption, and that comes from the fact that the total spectrum is sum of contributions of individual atoms. And this is because in the final state, there is a core hole that is left behind. And so each final state can be labeled by the atomic label. So it's not an approximation, it's an exact statement. Simply this sum over final states breaks up into sum over different atoms or different atomic positions. Now, to understand the symmetry of or geometry of XMCD experiment, meaning how does the spectrum depends on the direction of incoming light, we can use the relationship between the antisymmetric tensors and pseudovectors in 3 dimensions. So the XMCD is basically given by this antisymmetric part of the conductivity tensor at X-ray frequencies, and these can be concisely expressed as this what we call generalized Hall vector. And the dependence of the XMCD on the wave vector of the incoming light is expressed by this dot product between the generalized or frequency-dependent Hall vector and the direction of the incoming light. Now, the important and interesting thing is that this Hall vector, of course, depends on the direction of the moments in your sample, and in altermagnets, this dependence is particularly strong. So let me start by the first results, and this is the first observation of XMCD in altermagnets or on collinear compensated magnets. And the material here is manganese telluride. So let me briefly mention what manganese telluride is. It is a mode insulator which crystallizes in this inverse nickel arsenide structure. And you can view the structure as layers of manganese atoms which are ferromagnetically polarized and are anti-ferromagnetically stacked. And the geometry of the experiment is kind of unusual, especially if you come from the XMCD or from the ferromagnetic community, because in ferromagnets, when you measure XMCD, usually have the light coming along the direction of the moments, or if it comes at an angle, you usually interpret the spectra as the projection of your wave vector onto the direction of the moments. Here, the light comes perpendicular to the moments. Okay, so this is the geometry of the experiment, and this is a comparison of theoretical. Well, I'm kind of proud to say it was a prediction. Also, we published the data together with the experimentalist, but this was this comparison of theoretical calculation with experimental measurement, and the experiment was done in a way that the sample was cooled in an external magnetic field along the z-axis, the 6 Tesla field. Then the field was switched off, and the spectrum was measured. And depending on whether the field was pointing upwards or downwards, the spectrum had an opposite sign. And if you measured the spectrum with the field on, it okay, show this, and yeah, if the field was left on, the spectrum had a different amplitude and completely different shape. So where does this come from? So let us look at the individual contributions of the 2 magnetic sublattices, and let us first look at the more usual configuration when the light comes parallel to the magnetic moments. So if you now calculate the contribution of the 2 sides, you will find that there is a very large effect, because we have a d5 fully polarized d shell, spin 5 halves. So there is a very large individual contribution of each of these sublattices, but they exactly cancel each other. So there is no XMCD in the sample. This contribution is isotropic in the sense that if you rotate the magnetic moments and you still measure along the direction of them, the spectrum changes just a very little. And this is also something that's well known from ferromagnetic materials. And yeah, the effect is very large. So this is what you see here is actually the absorption spectrum for one polarization, the absorption spectrum for the other polarization, and this is the difference. So it's of the same order of magnitude as the spectrum itself. Now, if the light comes perpendicular to the moments, what we find is that now the two atoms, the contributions of the two atoms are added because they are related by this pi rotation, 180 degrees rotation. And of course, if you just rotate the sample or the structure along the direction of the incoming light, it's nothing changes for the circular polarization. Second observation is that the effect is much smaller. It's order of magnitude, or maybe even 2 orders of magnitude smaller than for the parallel contribution. So it's additive, it's small, and it's very strongly dependent on the direction in which the moments are pointing. So actually, if you rotate the moments along the full circle, you would find that there are 3 maxima and 3 minima with the same amplitude but opposite sign. And there is a node, there is a 0 in between, and this is 0 like uniformly for all frequencies. So this is a frequency enforced vanishing of the effect. So it's strongly L-dependent. Now, when the first measurements were taken and compared to the calculations, we found that there is a factor of 10 mismatch about the amplitudes. And actually, it was impossible to measure the spectra without cooling in the field. And this was realized early on that this is because there are magnetic domains. And so we have, in principle, we have 6 easy axis domains that they all produce the same XMCD spectra, but 3 of them with positive sign and 3 of them with negative sign. So if you have an equal population of these domains, you measure nothing. But cooling in the field basically causes a domain imbalance. You either favor the red ones in this picture or the blue ones, and that's why it's possible to observe the signal. Well, later on, the similar technique, XMCD in PEAM, combination of XMCD, circle diachroism, and linear diachroism, actually was used to visualize, to make the pictures of the domains in this paper by Amin and collaborators, and they could beautifully visualize all the six different domains in the manganese telluride samples. And there were also measurements that were able to measure XMCD in single domain systems, and there the theoretical amplitude and the experimental amplitude actually matched each other. And there are these 2 papers from different groups, different techniques. Okay, so one of the interesting questions is what is the origin of the XMCD in particular in this unusual geometry, and what are the necessary terms in the Hamiltonian to observe the effect. So this was originally, it was kind of numerical experiment where we singled out the part of the Hamiltonian where the valence spins can freely rotate. So basically, if you switch off the spin-orbit coupling in the valence band, and you switch off the exchange coupling between the core states and the valence states, then the Hamiltonian is invariant under arbitrary rotation of the valence spins. And interestingly, if you look at the XMCD for the K coming parallel to the moments, well, the spectrum changes a little bit, but the effect is still there and the amplitude is comparable. And this is something, again, which is well known from ferromagnets. And that's the fact that the key interaction is the spin-orbit coupling in the core states, which is a huge effect. It's essentially a kinematic constraint. It's the spin-orbit splitting is order of 10 electron volts. On the other hand, if you look at the experimental geometry where the XMCD is observable in manganese telluride, if we switch off these two terms, we get exactly zero. And this I will later show you. This is zero by symmetry, and this is because, as I explained, this Hamiltonian or this model now has higher symmetry. We have the free rotation of the valence spins. Now, if you turn on the spin-orbit coupling in the valence states, it brings very little. So it's not non-zero. The symmetry is not there anymore, but the effect is tiny. So it's the core valence exchange interaction which basically gives you, or is necessary for the effect to be observable. Now, let me go to the next system, which shows, as I will show you, the opposite behavior, and these are rutile altermagnets. So ruthenium dioxide is a prominent example, but as we know now, the material is probably not magnetic. But there are these transition metal difluorides, where we know for sure that these are very good antiferromagnets or compensated magnets, and these were well studied in 60s. And most of the materials in the series have easy axis along the C direction. And in this configuration, XMCD is forbidden for any direction of the incoming glide. And the symmetry reason is simple. The Hall vector transforms as an axial vector. And so if we have a mirror plane in mirror symmetry in our system, the only axial vector that is allowed must be perpendicular to this mirror plane. And so if you have more mirror planes that are not parallel, no axial vector is allowed. And this is actually the situation for null vector along the c-axis. On the other hand, if the null vector is in plane, then we can consider these two like higher symmetry situations where the null vector is along 1, 1, 0, so along the diagonal. And in this case, there is one mirror plane perpendicular to the magnetic moments. And in that case, the Hall vector is allowed, and it's perpendicular to the mirror plane, so it's parallel to the magnetic moments. If the null vector is along 1, 0, 0, then there is a mirror plane which is parallel to the magnetic moments, and in this case, the Hall vector is perpendicular to the null vector. And this is a situation which is experimentally realized in nickel difluoride. So it gets even more interesting. So first we found, basically by numerical experiment, and later we came up with symmetry arguments, that in rutile altermagnets, actually, if we have this higher symmetry where there is no exchange between the core states and we don't have spin orbit in the valence states, there is a simple symmetry relation between direction of the null vector and of the Hall vector. And this symmetry relation is simply a mirror relationship. So if you turn the magnetic moments in one direction, the Hall vector turns in the opposite direction, and there you go through the two situations I mentioned before. If the moments are along diagonal, the Hall vector is parallel. If the magnetic moments are along the square axis, along the Cartesian axis, the Hall vector is perpendicular. Now this is the situation when there is no this covalence interaction. We can ask what happens when these interactions are allowed. And what happens, and this is already the example of nickel difluoride, is that we get a canting. So we get a small ferromagnetic moment in plane. In nickel difluoride, this moment is around 0.03 Bohr magneton. And then you can make an ansatz, or you can ask yourself how much of this mirror relationship is retained. And so we assume that the Hall vector has this form, that it has an altermagnetic contribution, which where the Hall vector rotates against the direction of the rotation of the null vector if it's turned. And then there is a ferromagnetic contribution, which is proportional in amplitude to the magnetic moment, and it is parallel to the net moment as usual in ferromagnets. And we made, okay, so then when you rotate the whole structure, which you can do by applying an in-plane magnetic field at various angles, you would see two contributions which kind of turn in the opposite directions. Now, at first we asked, we didn't have any experimental data, so we just did numerical experiment. We did a full calculation, just ED, where we assume nothing and we just find what the spectra are. And then we tried to fit all these spectra with this approximate formula. So basically, for all possible orientations of the magnetic field, we have only two spectral functions, right? We have this delta altermagnetic and delta ferromagnetic, and we found that it matches very nicely. That within a fraction of a percent, this formula captures the behavior of the exact spectra. Quite recently, we got into a collaboration with an experimental group which was able to measure actually the XMCD on nickel difluoride. At the moment, they can only apply the magnetic field in one direction, but it's enough to extract this altermagnetic and ferromagnetic contribution, and the experiment and theory match each other quite nicely. I have to point out that our original theoretical prediction was somewhat different than the computational results that I show here, and this is because it turned out that the spectra are really sensitive to some terms in the crystal field Hamiltonian. So to explain this experimental data, we made some fine tuning in the parameters. We didn't use all the ab initio parameters from first principles calculations. So now let me briefly explain where this property, this mirror symmetry comes from. And this is what I would call a free valence spin approximation. So this is a situation where the valence moment can rotate freely, and this is actually something where the concept of altermagnet is really essentially exact. And what you can show in this case is that there is an exact linear relationship between the direction of the local magnetic moment, so this is a single side contribution, and the Hall vector. Okay, so there is some frequency dependent matrix that compare these two. Now there is a transformation that connects the two sides. For example, in rutile it would be rotation by 90 degrees. And so if you add up these two, you can get some linear relationship between the null vector and the Hall vector. And now, of course, the form of this matrix gamma depends on the symmetry of the system, and so and on this in particular on this omega A matrix, and yeah, then you use standard methods of group theory. These two vectors, magnetization and the Hall vector, both transforms as axial vectors. So you can ask, what is the allowed coupling between two axial vectors in this point group symmetry? And if you apply this to rutile, and this is quite intuitive, the single side contribution would have this form, right? Because the side symmetry is orthorhombic, so you will get essentially a diagonal matrix with three different spectral functions on the diagonal. Now, this is the rotation by 90 degrees, which connects the two. And so if you add up the two sublattices and you make a transformation by this 45 degrees to the coordinate system I used before, you end up with this relationship between L and H. And this is precisely the in-plane mirror symmetry between the Hall vector and the null vector. And there's one universal spectral function which describes this behavior. Okay, in nickel arsenide structure, just to make the long story short, the side symmetry is higher. You have a threefold rotation axis, so any rotation axis higher than 2 would give you the in-plane contribution to be isotropic. And then if you make any rotation, of course, this in-plane part doesn't change. It cancels out. That's why in this free valence spin approximation, there is no Hall vector in nickel arsenide structure. So, well, because I'm nearing the end of my talk, let me mention another interesting material, which is hematite, and hematite has actually very similar structure, at least the local structure, as manganese telluride, and it has an interesting behavior because below the null temperature, it adopts a magnetic order where the moments are in plane, and then at around 250 Kelvin, there is a reorientation, so-called Morin transition, where the moments turn along the c-axis. And so the high frequency, high temperature antiferromagnetic phase allows XMCD, it can host the non-zero Hall vector, while the low temperature phase cannot. It's forbidden by symmetry. Interestingly, there is a canting of the moment with a small net magnetization, which is pointing in plane. Okay, so then you can ask, what are we measuring if we measure XMCD? Are we measuring this ferromagnetic contribution, or are we measuring something altermagnetic? And the point is quite interesting. Well, actually, the large XMCD effect is measured when you come along the c-axis direction. Okay, so this means you're coming perpendicular to the magnetization, while this ferromagnetic contribution, where you come parallel to the net magnetization, is tiny. It's well, more than order of magnitude smaller. You can see it here. So this is the z component of the Hall vector, and this is the in-plane component of the Hall vector. This is a comparison of the calculated and measured spectra. The interesting point here is that the effect is about 10 times larger in manganese telluride, and you can ask where it comes from, because iron, it's in this material, and mangan in manganese telluride are isovalent, so we have spin 1/2 large high spin state. Well, the difference really comes from the crystal field splitting. So the crystal field splitting is the dominant effect, which dictates the amplitude of the effect here. Well, what is this good for? I mean, why are we interested in looking at the XMCD spectra? Well, the main kind of selling point is this microscopy. You can use XMCD and XMLD to map out the magnetic domains, but you have to know where to look. And that's why experimentalists come to us and ask, well, at which energy shall we measure? And this is a result of such a measurement. So this is a measurement in the low temperature phase. So in principle, here you see no contrast between the magnetic domains, but there is a domain wall. And you can see XMCD contrast in this domain wall, and you can see that there is even some texture in the domain wall. It means the moments are pointing in different directions in the domain wall. Well, as a side remark, let me mention that one can find also a contrast between the in-plane and out-of-plane orientation of the moments in the absorption itself. And it's quite interesting, because if you look at the total spectrum, there is almost no contrast anywhere except for this peak at the L2 edge, and where this picture was taken. So yeah, so let me skip bismuth ferrite and just go to my summary. So what I wanted to show you that XMCD is present in some altermagnets, and it's a very useful tool for determination of the orientation of the Néel vector. And nowadays, it's been used for mapping out magnetic domain structure in combination usually with linear dichroism. In XMCD, at least in the transition metal compounds, valence spin-orbit coupling usually plays a rather minor role in materials of interest. And so we can say the XMCD is really probing the ideal altermagnet, or it kind of separates the effect of altermagnetism from the effect of weak ferromagnetism due to Canting. And important point, even if these two contributions are there, they typically have a very different spectral shape, so they are quite easy to distinguish. So let me stop here and thank you for your attention.
We have time for a few questions, please.
What about Riggs?
Okay. So Riggs is quite interesting because Riggs has a very different selection rules from XMCD, and the biggest difference is that Riggs is not sensitive to time reverse symmetry breaking, in the sense that the experiment, the process itself, breaks time reverse symmetry. And so the consequences are that you can observe Riggs CD also in paramagnetic states. And another very interesting consequence is that there are states where the time reversed states, so with L and minus L, have different Riggs spectra, which cannot be mapped on each other by some transformation. This is kind of unusual. So what you can observe in Riggs and what you can study with Riggs is the unitary symmetries which you break when you undergo the magnetic ordering transition.
So thank you for the talk. I was interested about this Morin transition in the hematites. Do you happen to know why this happens in this material? Is this a structural change?
No, it's not structural change, but I don't know. I suppose that it's known, but I don't.
It's a spin reorientation.
It's a spin reorientation, but what drives it? It's not structure. It's not the structure that drives it, but I don't know if it is like order from disorder or what can it be.
Maybe one last question from me, if I may.
Give me if you don't want it.
As a theorist, I'm wondering, you showed terms in Hamiltonian with spin orbit coupling and with your valence coupling and quark. So, and you showed that one doesn't have effect and another does. Regarding the amplitudes, can we compare the amplitudes? They are more or less the same in the Hamiltonian, or one is larger for this compound? So
you mean comparing the strengths of the?
Yeah.
I mean, of course, the spin orbit coupling is weaker. Like the number is smaller, splitting would be smaller. It's one is 100 millieV, and the other one is 6-7 eV. But I don't know if it is a fair these two. But yeah, the splittings that you might expect are much.
Thank you. So one more question, please.
Thank you for that method. XMCD can the picture basically the domain walls, Altermagnets, were they overlooked before or misinterpreted? Because many of the materials are not started to do now.
Yeah, well, I think it's an experimental challenge, so it was not looked for. Of course, the important thing about altermagnetic domains is that compared, let's say, to antiferromagnetic domains. So if you would have a domain between L and minus L in antiferromagnet, it's really it's like a dislocation, or because you cannot distinguish the two domains on its own. They are basically identical states. While in altermagnet, if I give you the two domains separately, you can say, well, it's a different object, it's a different state. But I think that the reason why people are doing this now is experimental development, that they have the tools and they have also interest in looking at this.
Okay.
So
you could use it to look at the domain walls in detail, right? So you say you show there is one domain and the other domain, but in the rotation, probably you have the zeros of the.
Well, actually, you can see it here, right? There is, if you look at this domain wall, there is a structure, there is a contrast, which means that the moments are actually not along the c direction, they rotate, but they do not rotate uniformly, but there is like a wall inside the domain wall.
You look the same way if you look at the rutile altermagnets along with the spin along the z-axis, which should give you 0 eccentricity. Now, if you look at the domain wall, only the domain wall would light up.
That's right. That's right.
Okay. So let us thank the speaker again.
Okay, I will start now. Thank you, the organizers, for inviting us again. We was there last time was in Kyiv. As I mentioned, actually, it's my second. I was here after that workshop in Kyiv. Yeah, I visit my friend Yurko. Yeah, this is what I want to show. Yeah, that was last year. So this from Yurko, that's Svetlana Pondovich. She was also attending the workshop in Kyiv. After the workshop in Kyiv, we came here to visit, and it's very nice to be here again. And now I will go to start with physics. So I'm glad. This is a very theoretical talk, but so I apologize in advance for some of the slides that might be not so clear, but the beginning will be very clear. Yeah, very glad that Jan introduced the altermagnets already, so that's good. This not yet a paper, this talk is a collaboration with Jeroen van den Brink, who is here in the audience, and Toshihiro Sato, both from IFW Dresden. Yeah, we start lots of, in this talk will be about this map between a sphere S3, a three-dimensional sphere, and a two-dimensional sphere. So it's not a normal sphere, not like a fuzzy sphere S3, but it's a normal sphere. They are embedded in a four-dimensional space, here embedded in three-dimensional space. And the best way to talk about this map for physicists is maybe start with two-dimensional harmonic oscillator. The two-dimensional harmonic oscillator can be used to construct any spin state. So this is a well-known fact, but this will help us to go to the CP1 variables. Actually, I forgot to set my timer. I was saying all the time that I will do this. You check? I want to fact check you.
Sure.
So, okay, I talk for 1 minute already, but it doesn't matter. So I can do this change of variables, and then you will see that a constant energy surface here is a sphere S3, if you count the phase space, right? Momentum, two components of momentum, and the X1, X2. So quantum mechanically, you can use define P and X as operators, and you can define, as usual, annihilation operators, equation operators like here in the first line. And for two, you have needed two of them. You define particle number operators, but now you have two integers in the states, in their two-dimensional harmonic oscillator states. What is interesting, you can define, using this construction from a two-dimensional harmonic oscillator construction, define any spin. So using the Pauli matrix here. This is a vector of Pauli matrix. And this fat B here is B1, B2, the two components. The angular momentum states are just constructed using the creation operators, where any1 equals S plus M, any2 equals S minus M. This is the standard. This is to construct a standard basis of any spin. Here I have all the spaces, 0, 1/2, 1, etc. That's a way to construct a space. In this way, it's called Schwinger bosons. Is already pretty much what CP1 does, except the CP1 is more bridge between classical variables and quantum variables are not operators. It's a Hopf map, which we see in the next slide after this one. Because our main interest here will be to discuss a CP1 formulation of the quantum nonlinear sigma model, which is usually an effective model. It's a field theory model. That's derivable from quantum Heisenberg antiferromagnet to have this arbitrary, yes?
So this holds for integral models, yes? I mean, your example from one oscillator holds for integral oscillator.
Yeah.
Some nonlinear term that's not true anymore.
What?
If I add some non-linear term.
Non-linear term, yes, yeah. If I add an harmonic oscillator, this doesn't hold. No, that's absolutely right. Yeah, that's only for exactly solvable two-dimensional harmonic oscillator. Now, here for this Heisenberg, I can use the Schwinger boson representations. For spin 1/2, you have a hard constraint with the bosons. This has an obvious SU2 symmetry, but the main important point here that will be important for us is that there is also a U1 symmetry that you see only is a local U1 symmetry. You can do a site-dependent transformation. This is spin defined this way is completely invariant. Now, so in this talk, I will bridge between this type of descriptions for defining nonlinear sigma model from one dimension, from 1 + 1 dimension, one spatial dimension, meaning spin chains, it go to 2 + 1 dimensions, which is the case of antiferromagnets, of altermagnets. And then we'll see that there are actually many things that in common that might happen when you, especially when you study strongly coupling theory or quantum critical behavior. Now, the CP1 representation for the nonlinear sigma model, this is a classical effective model for the Heisenberg model. This is an O3 nonlinear sigma model. I put these ellipses here because you can have other O3 variant terms in general. And this is a free theory in principle, but there is a constraint which makes this theory non-trivial. There's a coupling constant that you have here. The Hopf maps, S3 to S2, is precisely like the Schwinger bosons I used earlier, except now these are like coherent states for the bosons, right? You write N in terms, you go from this S2 sphere, because there are only 3 components of N, to an S3 sphere, because each complex number here, each complex field here has a real imaginary part, right? You can consider even S times some arbitrary spin times the direction of the NL field. Now, what about the ellipses that I wrote there, right? So, first, when you write a CP1 representation here, you can plug this, use the algebra of the Pauli matrices. It's very straightforward to write this in terms of a theory that contains only the complex fields and a gauge field. This gauge field is there, it reveals a gauge invariance, a local gauge invariance that I saw before in the Schwinger boson representation. There is a local gauge invariance that's induced. But this gauge field is not an independent field. It's not a field that is at this level, right? At this level, a classical level. It's written in terms of this complex fields themselves. The reason it looks like a current, right? It looks like a current for these complex fields. The fact that we have this 2 writings here is because if you make the derivative of the constraint, right? To make the derivative of this constraint, you can see that this is minus this term. That's why it's like that. Now, at the quantum level, this gets a dynamic by itself. But at the moment here, we have completely classical, the classical field theory. Now, what about the ellipses? That's the part where it becomes interesting. That's the part where we bridge between what happens in 1 spatial dimensions, what happens in 2 spatial dimensions, what altermagnets have in common with that. The field theory for the spin chain, right, is it's from the Haldane field theory for spin chains, is a topological nonlinear sigma model. It contains an additional term. It's called a theta term, which is derived from Berry phases from the spin part integral, right? And this theta term, that is quite intriguing. This is what part of the Nobel Prize Haldane got. It's because of this theory. Interesting, there are many things we still don't know about this theory. That's where I will see also that there are many things we still don't know about also the magnets in this context. This theta, this is a topological term. This is a total derivative actually, but this influences the spectrum of the spin waves. Where this theta is 2 pi s times the spin, and then you find out for integer spin you have a gap in the spectrum. In 1 + 1, half integer spin, the spectrum is gapless. So, this means if you take theta equals pi, this is that theta equals pi, spin 1/2, you have this is completely not obvious, right? So this has a gapless spectrum. This has experimental confirmations in several materials. Now, how is this written? Well, before let's put remind some facts that I will not be able to talk in detail here. First, this topological action that is here, this associated with this L theta, this Lagrangian, is independent of the metric. This is the reason why it's topological, right? This doesn't affect the field equations. Right, because independent of the matrix, it doesn't appear in the field equations. The field equations are just like the theory which contains only the first term, not the second term. However, if you it does change the boundary conditions because the topological term is a typical thing. If you have boundaries, you modify boundary conditions. You can have, for example, in this theory, you have some things that I will not talk about here, for example, fractionalization of the spin. And interesting aspect is if you do renormalization group, you don't see this theta term there. Now, if you do a renormalization group, this means you integrate up in this the high energy modes. You take divide lambda, the upper cutoff by L, integrate the fields associated with these high energy modes. You get an effective theory. What you try to do is to map to the original Lagrangian when you do these steps of renormalization. You see, you make a scale transformation in the system. You see how the system responds. So they measure. A theoretical experimentalist. I do a renormalization group. I judge the scale. You see what happens on the other side when I change the scale, right? Like a finite size scale on the paper, right? So I do that, and then what you get, you modify. You try to get the same Lagrangian as before. You modify just the coupling constant. The coupling constant that you modify becomes. Has a dynamical equation where L is this scale here. Is this scaling factor? What this equation gives is always gives a gap. So because this topological term doesn't affect this equation. So if you try to solve this equation, you get a gap at things. And moreover, from this equation, G will grow with the scale. So this is something bizarre. So then it comes to the Haldane conjecture, because Haldane showed something about the spectrum. He derived the topological action to modify the Hamiltonian, which contained a quantum term. This changed the solutions for the spectrum. And then for theta equal pi, he showed that was gapless. Now, here, then it came with this conjecture that we still don't have a full proof. That there is a more symmetrical theory, a higher theory, which I will not talk about here. There is actually a very important paper by Flavio Nogueira about that, which is based on this first paper about no-abelian bosonization. So you just take a theory which is more complicated, has a larger symmetry group. The idea is that when you do this renormalization step, you try to get the same theory as before. What they are saying, Flavio Nogueira say. No, we don't get the same theory. You get another fixed point, another theory which is not this one. Would explain why you have this. So why you don't see the theta term here, right? Because this is you are in a submanifold of your normalization space, right? Now, if you do a CP1 version of Haldane model, you see something very interesting. This theta term looks like an electromagnetic some kind of anomaly. But in 1 + 1 dimension, that's why you have only this mu nu. There's a quite easy calculation to do with the things I gave to you in this slide, right? It's just algebra. There is nothing complicated there. This is a low dimensional version for the well-known theta term that appears here. This gauge field is not electromagnetic field, but there is a theta term that appears, for example, in topological insulators or Wire-Sam metals. Topological insulators is really like that. Theta is a constant. It's a topological term like this term, because it's dependent of the metric from this side of this theta term. You can see this because it's written in covariant form. But in terms of electric magnet field, this is just a E dot B term, a magnetoelectric term, 3 + 1 dimensions, right? So this is a total derivative as well. They're just like this term. So you can see that this doesn't. Another question is what happens if you derive something like that for altermagnets, right? What you do? What is the nonlinear sigma model for altermagnets? There are several types of lattices. There are all types of checkerboard lattices, but one that very popular lattice that for doing that is the Lib lattice. The Lib lattice, so you can construct from the square lattice, the standard square lattice, which where the points of the sites B, C appear in the bonds of another lattice, another square lattice, which contains those blue sites A. Now I have 3 atoms per unit cell. So if you go, the lattice depends what happens. There are some things you have to say. Is the lattice is not everything, not the whole story. You have to say what is going on when you have a hopping or your exchange coupling. And in this paper by Lib, which popularized this name, Lib lattice, he's considered only bipartite. Okay, it means that every hopping in the Haber model go from different sublattices, one, for example, B and C. If they show for half filling, for example, the square lattice from Lib's theorem, you get an antiferromagnetic state. You can lock spin up to sublattice B, lock spin down to sublattice C. Now, if you try to do this, but maintain this being bipartite in altermagnets, this doesn't really work because you get, as Lib mentioned, you get a ferry magnet, not what we now call altermagnet. For this, we need that this sublattice A is non-magnetic. You need also to make this non-bipartite to stabilize the altermagnetic ground state. We get those spin splitting bands, right? Now the question is, you can use like in a lattice of the type of ruthenium oxide that was mentioned in the previous talk also to derive a Heisenberg model like that. The point is, you arrive to this type of, if you use that Lib lattice or any other checkerboard lattice which is compatible with the altermagnetic symmetries, with the symmetries which are typical of altermagnet, otherwise it doesn't work. You get this additional term here. Sorry, I changed it from real time to imaginary time. You get an additional term, which seems pretty much like Haldane, but with an additional derivative. Instead of, remember, Haldane didn't have, here we have one more dimension of space. Now we have a double derivative, we have a mixed derivative. This was derived recent 2 years ago In this paper, it's actually the supplemental material, I believe. It's a supplemental material inspired by the ruthenium oxide lattice. They use it. They derived the field equations using Landau-Lifshitz equations. It then, like you can derive also from the Lib lattice in the way Haldane, that's the interesting thing. If you do the way Affleck, Haldane do with the spin path integral, using the Lib lattice, for example, you get exactly the same term. Now, the funny thing is, so I mentioned the similarity with the Haldane, with one more derivative. It turns out if you, the presence of a boundary, right? If you take this in presence of a boundary, you get precisely on the boundary a Haldane type of term. The point that is lambda here is not quantized. It's not taking that in Haldane cases. Remember this theta, there was theta over 4 pi, right? This is not quantized, but maybe this forces the question, now it's a question mark. This may forces this to be quantized at the boundary, but it can be also zero in the boundary. We don't know for sure. I don't know the complete RG for that. The RG we did last time in the bulk, this is a paper by collaboration with Asler, who is sitting here in the audience with his student, Sondra. When you do RG, remember that in Haldane case, there was only this formula without the minus G. There was G squared over 4 pi. It was given only gap in spectrum, right? So if you do now the same thing, if you take an Altermagnet, so the G is not dimensionless. You have to rescale this with the UV cutoff, define the RG equations for dimensionless G, right? And you have to find the equation for lambda. Lambda, on the other hand, is dimensionless for the beginning. Now, the point here is that these equations predict the following, that, well, here first I have a fixed point. A fixed point is not a zero. I don't want you can say, okay, this is a gapless state, right? But if you are near this fixed point of 4 pi, you try to solve this equation near this fixed point, you see that lambda flows to zero near the fixed point. It's a irrelevant operator. This was our conclusion at the time. And the question is that the whole story? That's the point where you will go to now to the CP1 Altermagnet finally, because I see myself running short of time. I need 2 minutes more. 2 minutes? Can I have? Yeah. Okay. If you do these things, well, we'll see. Now there is one thing that's deceptive. I don't get a topological term when I do the CP1 transformation like we did for the Haldane case. I get a much more complicated term. I got this term which contains, well, here I introduce a notation to be more economical, the covariant derivative. And this means I have a very complicated interaction with the gauge field. So no topological term is generated so far. I was hopefully that I would do this, but I didn't. I actually mentioned this in the abstract, but that was incorrect, unfortunately. Now the question is, what you can do with this? The advantage of using this formulation is that here I can generalize to any components complex field. So here I lock it to O3 because of this symmetries of this object here, right? Now, if I do a saddle point approximation, a calculation of saddle point approximation, here is a case as a finite temperature, but I will not use it here. You get this type of gap equation from the saddle point approximation. I'm omitting details here, of course, but it's not a difficult calculation to do. This is spectrum. This is typical Altermagnetic spin wave spectrum with a gap here. But if you put the gap equals 0, is really the Magnus spectrum. And now the question: what kind of phase diagram this gives? Now there comes a surprise. It gives a phase diagram. It's not RG. It will give a phase diagram that also shows that G grows with lambda now because there is a second coupling. If you do numerical calculation of this, because this integral is we are not solved exactly, unfortunately. The perturbation theory here is very tricky, is very badly behaved. The reason I'm showing those two plots, they're the same plot, but one is G, one is 1/G. So there is only two phases here, altermagnetic, paramagnetic. I don't know if there are more, but you see that G critical, this is the line of G critical, this is growing. Like in Haldane case, right? Like in Haldane case, this is growing. I think, okay, maybe not so bad, because if you look at 1/G, the 1/G decreases. If you compare with the Lagrangian, if lambda is growing, so this, I can neglect this. I can get lambda infinite. We forget about the first term, right? So, but this is too naive. Why is too naive? Because I know from Haldane already that this type of thinking is too naive, that this maps exactly by the RG in the same action, right? So that's the question, though. Will this require some type of non-abelian? I mean, by this I mean a higher symmetry thing, like UN times UN symmetry, like Witten term, which I not consider here, but as the thing you got from the RG doesn't seem to be totally compatible with the phase diagram from saddle point approximation, which I could also do with the nonlinear sigma model, by the way, right? So that's the main message of this talk, is that perhaps I think that one of the most important points to highlight here, also because of the fact that you have this Haldane term at the boundary, is that you might have a very interesting phase structure because of a more intricate normalization of the Altermagnet term. Thank you for your attention.
Thank you very much, Flavio. So we have time for questions. Perhaps I could start. Do you consider also extensions to high symmetric models like SU3?
No, not. But that's one of the. Well, there is a SU3 in some sets, right? So it depends what we're calling SU3. For example, because there will be a SUN symmetry when you make this transition, right? This is something you cannot do in the nonlinear sigma model language, but there is a matter of interpretation, because then there's a mathematical type of altermagnet that we don't know to what it really corresponds to. That's the point. Because this, even the nonlinear sigma model, right? The map CP1 this Hopf map is only exactly the same for O3. The CP2, I don't know, is something else, right?
Right.
But there would be a way of doing this, but there are other ways via the vast domain entirely.
Okay, thank you.
There's a question.
Second question. To what extent is analog to the speed one can be taken? Yeah? So we think about speed one in many different contexts, edge states, Alkali interpretation of some kind of axion with speed one hard objects. How much we can take this and rephrase it in altermagnetic language?
Well, the altermagnets, they're actually, well, when I talk about this most of the time is spin 1/2, right? So, but this is for the electron. The question is the spin. We'll probably talk about the spin of the magnet citations, for example. And the question about CP1, an additional question about this, the magnets will have a spin 1 objects, right? So, but one of the questions that happen, it actually happens in the Haldane case. It might happen here also in altermagnets. That's why I want to use this formulation. Is a possibility of fractionalization, right? In the Haldane case, we have spinels with the Z's become real excitations, physical objects, right? So the magnetic moment falls apart, right? Those objects have spin 1/2. These are the spinels, right? So that's the answer, if I understood correctly your question. Yeah. Yeah, also.
There was no fractionalization in your favor.
No, not here. I don't have time to talk about this. This is already.
Is there
Yeah, absolutely. That's what that was originally the idea.
So the large is one of these examples of these ellipses, like that people write down and never specify.
Huh? What?
So your expertise in Lagrangian, your
Yeah, well, yeah, exactly. Some interaction. So you can add some. Like you are thinking about the JQ model, for example. Yes. The question in the labs, you don't know how to do this yet, but that's a that would be that's a SU2 invariant interaction, which can lead to valence bond crystal spaces, etc.
Okay, thank you. We need to move forward.
Okay. Thank you.
The next contribution is from Katerina Witteveen. Anisotropic magnetic properties of alkali metal intercalated layered chromium telluride.
Thank you very much. So welcome to my talk. It's a very exotic talk in this session because I'm going to talk today about the crystal synthesis and specifically about the anisotropic magnetic properties of these alkali metal intercalated layered chromium ditellurides. So here you see the crystal structure, and basically what you have is a covalently bound chromium ditelluride sheet that is intercalated with alkali metals. So namely the potassium, the sodium, the lithium, and then the intercalated chromium ditelluride, which is the only bulk magnetic transition metal diaconite that you have. So brief acknowledgements. This is the result of my PhD work that I did back at the University of Zurich and University of Geneva under the group of Fabian von Rohr. And I want to especially emphasize the fantastic collaborations we had with Martin Manson from KTH, whom some of you might know, and who brought me actually to this project. So a brief outline, I'm going to start with the lithium chromium ditelluride because it has grown this way historically. And then I want to make a quick excursion to the chromium ditelluride, not only because it's part of this model system, but also because the synthesis is quite interesting to access this chromium ditelluride. Very brief magnetic properties of the sodium and the potassium chromium ditelluride. And if time allows, I want to actually show you some results of the diselenide that we have obtained, and that gives a very nice outlook of all the work that still can be done, synthetic work. So the initial motivation actually was coming from two publications back in 2016. So there was an observation of the strong magnet-phonon coupling via inelastic X-ray scattering in lithium chromium dioxide. And then there was this first-time report of the lithium chromium ditelluride, which was synthesized by Kobayashi and co-workers. And I think that's might be here a bit the more interesting point for the theorists, right? So they were interested in the difference in magnetic properties of the isomorphic lithium chromium diselenide and ditelluride and sodium chromium ditelluride. And I want to go a bit more in detail about the background and the motivation of Kobayashi and co-workers. So they were really interested in studying this two-dimensional triangular lattice compounds because they host quite exotic ground states and physical properties. So why triangular, right? So you have a triangular lattice of the chromium in plane. And so for instance, we have the water intercalated sodium cobalt dioxide that becomes superconducting, right? When you have water in between the layers, but then you have also multiferric copper or silver iron dioxides. And so especially when you look at these chromium dioxides, the intercalated ones, they exhibit this classical ground state of Heisenberg triangular lattice antiferromagnetic magnets with this 120-degree spin structure. So, and in these oxides, you have a much stronger direct or antiferromagnetic direct DD exchange of the chromium-chromium atoms, which is much larger than this ferromagnetic chromium anion chromium super exchange. So this is known also as the Calamari-Anderson rules, and I believe many of you might know these. And so the interesting thing is that when you go to the sulfides, you get a much more flavorful magnetic properties. So you start to have a competition between these two interactions, yes? So you enhance the chromium-chromium distances because of the larger size of the chalcogen, which results in the lithium-chromium disulfide being the 120-degree spin structure, but the sodium-chromium disulfide already becomes this incommensurate helical spin structure, and the potassium chromium disulfide then has this A-type antiferromagnet, but with ferromagnetic nearest neighbor interactions because of the favorable ferromagnetic chromium anion chromium super exchange, which you see here. So that was the motivation of Kobayashi to synthesize the tellurides, because they were not studied at all, okay? Because they're very difficult to synthesize. So the bigger your chalcogen, the more sensitive your material becomes, okay? So they synthesized it, they managed to do, and they found a transition temperature of 70 Kelvin and believed it might be of a helical spin structure. Why? Because it's very close to, you have rather large chromium-chromium distances in the compound. So definitely not 120-degree spin. So Martin came and was like, okay, we want to measure the magnet-phonon coupling in lithium-chromium diethylamide. Sounds very interesting, but we also want to elucidate the crystal structure, the magnetic structure. So can you please synthesize, right? And then I did, okay, I will. And so I managed to make this lithium-chromium dioxide, and this was work done by the Elisabetta Naturina from Martin's group. So she found it actually to be A-type antiferromagnetic, like the potassium chromium disulfide, but she also found a very like a negative thermal expansion. So if you cool down the temperature, the chromium-chromium distances in plane, they start to expand, right? So this is quite an interesting phenomenon, but also a strong lithium, a strong spin lattice coupling. And MSR results that she obtained revealed a Néel temperature of 128 Kelvin, so much higher than 70 Kelvin that were previously published by Kobayashi and co-workers. So here a brief synthesis slide. So how do I make them? I started to, of course, to trials with the powder. So what you do is you put the elements in a, well, you work under the glove box because lithium is very air sensitive. You put everything in a crucible, in a quartz tube, and then you seal this quartz tube under vacuum. And then you heat it up to 700 degrees in the case of the powder. And then you remove it, you quench it at room temperature, and then you get this black lustrous powder, okay? But so what we aim always is to get single crystals. And so I was trying to do some lithium tellurium fluxes. And you have to know, so this lithium is attacking the quartz glass quite intensively. So you get a glassy phase, so the quartz impulse breaks. So it's quite a tricky synthesis. But I managed to grow, or we managed to grow the single crystal using this excess lithium and tellurium, which is absolutely fantastic because then you can start to do orientation dependent magnetization measurements. And what we found was quite a strong anisotropy. We did magnetization versus temperature and field measurements. We observed the spin flip along the easy axis around 2.5 Tesla, made this phase diagram. But we also observed a third transition temperature or Néel temperature of 150 Kelvin, right? So now we have the same material, 3 different transition temperatures. So something is not coherent, right? So as a brief recap for the lithium chromium diethylamide, okay, we discovered that we can make single crystals with this mixed alkali metal chalcogen flux, but we have these different Néel temperatures, and let's keep in mind why. Okay. Change of compounds, chromium ditelluride. So I told you, right, that it's the only transition metal dichalcogenide that is magnetic in bulk, but we cannot access it directly. It's a metastable compound, so it's a D2 system. So when you have the splitting of the orbitals, it's T2G, EG orbitals, right? And chromium of chromium ditelluride is a D2 system, so it has 2 electrons. it doesn't like it. So what you do, you start to synthesize the intercalated compound directly. And we can nicely see it, right? When you have a saturation of the when we have a saturation of the magnetic moments, we are around 3 mu Bohr, magneton Bohr, right? And when we de-intercalate it, then remove this alkali metal via acid, with acids or with iodine, work done by Kai from my former group. Then we get this chromium ditelluride, and you have an effective magnetic moment of 2 Bohr magnetons, right? And the interesting thing here to note is that the spins, so it's an overall ferromagnetic structure, not antiferromagnetic anymore, but the spins lie in plane and much higher transition temperature of 380 Kelvin. Sodium chromium ditelluride, so we made the single crystals with this mixed alkali metal chalcogen flux. We found an antiferromagnetic structure at 110. And then potassium chromium ditelluride, that was a paper that was laying around quite for a long time, or like a project, because we didn't manage to solve the crystal structure. And it's imperative to know what kind of crystal structure you have in order to start to analyze your Newton powder diffraction data, right, and stuff like that. So Felix, fantastic crystallographer from my former group, managed to solve it, and we found an overall ferromagnetic structure with a potassium deficiency, but a Curie temperature of 117 Kelvin. So brief conclusion here. So this intercalated chromium ditelluride system is really a model system to see how the magnetic properties and the are affected by the crystal structure and vice versa, right? We have the strong lattice, spin lattice coupling, and we can actively really change these intra-distances and interlayers, so interdistances and interlayer distance with the different alkali metal. This results in these different properties. And so while the Goodenough, Kanemaru, and Anderson rule predict the nearest neighbor in plane magnetic interactions, I still don't really understand what makes the spins like in plane or out of plane in the system, right? And for me, like creating or synthesizing these model systems where you can experimentally access actually trends is the main part of my work as a synthetic chemist. So I have 1 minute left to briefly give an outlook what we still can do with the system. So this was work that we published on the potassium chromium diselenide. So again, we tried this mixed chalcogen selenium flux, and well, I'm not a very good crystallographer, but I hold this in the SXRD, and what I saw was very weird spots. And I left it aside. And then when Felix arrived in our group, I gave it to him by mistake, actually. So it was pure serendipity that we published. And he was like fascinated by the structure. Okay, cool. We have satellite peaks. That means we have an incommensurately modulated crystal structure. We have undulated chromium diselenide layers intercalated with potassium. And it's the potassium deficiency that actually drives this undulation. And potassium chromium diselenide also had 3 different published transition temperatures. And so what he further found was that you can actively change the amount of alkali metal in the structure and the phase formation with the quenching temperature, right? So a high quenching temperature or a low quenching temperature in this compound yields a fully stoichiometric intercalated phase with a much lower Néel temperature than the partially intercalated phase at 133 Kelvin. And then you get even lower potassium content when you centrifuge it at high temperatures. So as an outlook or brief conclusion, we can grow the single crystals with this mixed alkali metal chalcogen flux, and the centrifugation temperature controls the structure. So now we can start, I mean, for me as the next project, would be nice to see if we manage to synthesize the full stoichiometric potassium chromium ditelluride and see where the planes lie, right? Do the planes lie in plane because it's partially stoichiometric or because it's full? I don't know. And so deficient alkali metal equals higher transition temperature. And of course, we find very interesting crystal structures in this material or model system. So, and then I want to thank, of course, Sabine, my new group leader at IFW, for letting me come here. And then thank you to the organizer, to Jürgen van den Brink and Bernd Büchner, and to the Ukrainian team for letting me speak here. Thank you very much.
Thank you for the wonderful talk. Please, questions? Yeah, perfect.
Thank you, President, for the excellent talk. My question is a little practical curiosity. When you talk about lithium compounds and the fact that they are chemically aggressive and attack the quartz atom, I'm wondering how did you manage to protect it from that? Was it some coating or?
Well, I could have done the coating, but what I did is I put them in alumina oxide crucibles before. So I used this Canfield setup. I tried to draw it actually here. Yeah. So we put them in these crucibles, right? And then we have the sieve in between, which is designed here. We have the toplet, and then we flip it. So I removed at 550, I removed the quartz tube, and I flip it. But even though you have all, I mean, you have the lithium going into, I mean, still attacks, the fumes still attack the glass. So I have to be very fast and putting it in the glove box really fast. So yeah.
Thank you.
Thank you.
Nice data, nice crystals. Which ones of those can be measured by artists in could be measured, already measured by?
Yeah, well, it's a nice question actually. So I call them, they're not two-dimensional, right? So you have they are intercalated, and you have cationic or ionic forces holding the layers also much strongly together. So I cannot exfoliate them very easily. So we could think about exfoliating the chromium ditelluride, but what I think happens in the chromium ditelluride itself is because it's this D2 system, right? It oxidizes very fast in air, first of all. And then whenever you manipulate this chemically, you get a lot of defects in the crystal structure. So it was very hard to exfoliate. Maybe also a reason why it's difficult to exfoliate is it's ferromagnetic room temperature, so the layers want to stick together. But yeah, we never managed to make nice exfoliated layers. Well,
Just to clean.
it's just to cleave, yeah. Well, maybe it would be interesting actually to have it. So the largest are about 7 millimeters in huh?
In straight direction?
No. The top layers like 1 millimeter. I can achieve more, but I can tune the size. So if you ask me, the shape and the size, yeah.
So they're metallic.
So yes, they're metallic, especially the compounds that are deintercalated, right? So you go from a filled half orbitals to an even more or less filled, right? So I guess you have more electrons that can swim around. Yes.
Yeah, just wanted to ask, my dear, I already asked you, did you try to use optical floating
To grow?
Yeah, to grow. But it's not needed, it works.
I'm not acquainted to the floating zone, but I believe that the problem could be the alkali metals in it, right? So I'm not sure if it would work, but I need to ask Sabine. I mean, it's not something that I'm acquainted with.
Very nice.
Yes. Why are you asking about the floating zone?
They gave us one to Ukraine.
Yeah.
We can do it in Ukraine.
But you want to do big crystals because why? Because it's nice to have them. Okay, good. Yeah. Well, I mean, we have neutron data, MESR data on all of the compounds, neutron data on all of the compounds. The talk was a bit short, so I didn't show everything, but yeah.
Okay. Yeah. Undulation is very interesting. What is the length scale of this?
So,
Is it really on a microscopic scale? Or-
well, we don't see it. I mean, I didn't see it by eye. But so let me see. I don't have the big unit cell, but I think,
Just a length scale of this appellation.
yeah, I think it's a 18, I mean, it's a supercell, 18 unit cells wide. This is what I have in mind. So it's rather big. Yeah. Yeah. And I found one paper from 95 where they found an undulated layer also in lanthanum chromium trisulfide. So I've never seen something like that before. It's quite interesting also how it affects, right, the magnetic properties. So that was a big question in the beginning. Do we have a higher Néel transition temperature because of the undulation or because of the deficiency, right? We didn't know. It was really a historical project, basically, finding a lot of findings on the way.
Okay, thank you very much for your presentation. And concluding contribution is in this morning session from Anastasiia Chyzhykhova, Feynman paradox in axion, insulators, and superconductors. Please.
Yeah. Very good. Thank you very much. Yeah, my name is Anastasiia. Today I want to talk about Feynman paradox in topological insulators and superconductors. This is the work done with Jeroen and Flavio. Yeah, and with this I would like to start. A small outline before I start. So I will start with showing the effective theta term, which Flavio has already shown today in the framework of topological field theory, which is utilized to describe electrodynamics in various topologically non-trivial materials. Then I will proceed with our problem at hand, which is spherical topological insulator in the presence of an outside point charge. We will solve this problem for static field profiles, and then we'll derive some interesting results, including rotation of the sphere, of the TI sphere, deriving the induced angular momentum there. And then I will conclude with a brief mention of analogous effect connected to rotation in superconductors. So this is the already seen today term. This is a so-called axion term. It's just coupled magnetic and electric fields with coupling theta, which is generally field, but in the framework of TIs, topological insulators, it's equal to pi in the bulk, and is basically a Berry curvature in momentum space associated with the band structure of the crystal. This term can be derived in several ways. It arises, for example, when analyzing wild semimetals and 3+1 dimensional TIs. Now we use it. Here's the Lagrangian, very simple. So the first term is a Maxwell term, and the second term is axion term. Alpha is the fine structure constant, theta is equal to pi in the bulk of the sphere. Here's this point charge outside the sphere at a distance d. And so as a consequence of this axion term, we observe that an electric field from the point charge makes the axion generate the magnetic field, and therefore, and vice versa. And therefore, we have a non-zero angular momentum due to the fact that the Poynting vector is non-zero. Therefore, yeah, we have a non-zero angular momentum. Here we also observe that this magnetization is proportional to the electric field. And it's useful to mention that in our case, the magnetization is not spontaneous, unlike in a ferromagnet. And changes in it, in magnetization, they occur by varying the electric field, and this in turn is achieved by changing the position of the point charge outside the spherical TI. Here, the unusual result observation is that the electric fields induce magnetic ones and vice versa, even in an inherently static situation when, yeah. And there must be an angular momentum being generated as well within the static framework, which brings us to the notion of Feynman paradox, which was first mentioned in the lectures, in Feynman lectures, lecture books. So this Feynman paradox constitutes Feynman's disk. It's an insulating disk on a rod, can be rotated without friction. There are charged small metallic spheres on the circumference of the disk, and there's a small coil in the center with the DC current running through. When we change the coil current, the Lorentz force acts on the charges in those metallic spheres in the circumference, and therefore the generated angular momentum, due to the conservation of angular momentum, the disk rotates. In our system, however, varying the distance d will lead to the change in the electromagnetic angular momentum, and therefore this transfer of angular momentum and subsequent rotation of the TI sphere. This is just a small, spoiler, I guess. And this is how in the image charge method, we can solve this problem, and the axion term will yield magnetic and electric line charge densities extending from the origin of the sphere up to the Kelvin point, so-called Kelvin point, and then also from the distance d to the infinity. This is called the reflection point charge, and this is transmission point charge, and also line charge densities. The modified Maxwell equations in the static limit look like this, and we don't have a current source here. And rho denotes this outside point charge. It is proportional to Q, to its magnitude. All the fields are potential. Lambda corresponds to B being defined inside of the TI, and chi outside of the TI. Phi corresponds to the electric field here. The subscript plus denotes the potentials being defined outside the sphere, and minus inside. The ansatz in this spherically symmetric problem is we basically expand the potentials in terms of the Legendre polynomials, and we just solve this problem for the coefficients using the following boundary conditions. We have the coefficients over here, and we see those corrections in terms of this axion coupling. Those magnetic coefficients, the coefficients that correspond to magnetic potentials, they are they are corrected in the first order of this theta coupling, in the first order of fine structure constant, which is a leading contribution. And here they are, beta and alpha. We can now easily calculate the magnetic line charge densities, reflection and transmission ones, using the following relations, and the same also can be done for the electric potentials. Result, however, does not differ appreciably from the trivial insulator case, so we do not show them here. Due to the rotational invariance, only one component of the electromagnetic angular momentum survives. It's the z component. And here's the Poynting vector that I've mentioned. So we just plug everything in, all the calculated potentials. After simplification, we get this short expression. And I point out that this angular momentum is proportional to the Planck constant, as well as it also scales with this n capital. And n is the number of elementary electron charges in this Q charge outside the sphere. Upsilon is this function that cannot be brought to closed form and depends on this ratio d over a, where d is the distance to the point charge and a is the radius of the sphere. Now we plot this angular momentum dependence on the ratio d over a. It is linear in the log-log scale, implying the power law dependence. And yes, due to the conservation of angular momentum, when we change the distance, it would yield the rotation of the sphere, therefore. An analogous situation kind of can happen in a spherical superconductor. So if we consider a non-Weil, a regular superconductor, without any applied electrical or magnetic fields, if we rotate it about a z-axis, it leads to the generation of the electric and magnetic fields, and therefore to a non-zero angular momentum. We then solve the field equations, and we find out that deep in the bulk, the induced field does not vanish, and it is proportional to omega, so the frequency of the rotation, linearly. However, it has been shown in this reference that by Vira and Flavio that in time reversal broken Weil superconductor, when you rotate it, a spherical TRB Weil superconductor, in an analogous setting, you would get the following solution for the B deep in the bulk. And we can see that there is a critical frequency at which the magnetic field vanishes deep in the bulk. And therefore, we have some sort of perfect diamagnetism here. This implies also an experimental way to probe an axion coupling. So this talk is based on a published PRB paper, and here, you can check it out if you want, called Feynman paradox in a spherical axion insulator, and it was dubbed editor's suggestion, which we were very happy about. So in conclusion, I just want to say that axion field theory can be used to describe various classes of topologically non-trivial materials and describe effectively continuous media electrodynamics within them. Then we have solved this problem and found magnetic line charge densities that arise in this problem due to the axion, unlike in the material sphere problem with an outside point charge. We have utilized the fact that static fields bear angular momentum, and the change in this distance to the point charge leads to the rotation of the TI sphere because of the conservation, a fundamental law of conservation. We discovered the power law dependence of found electromagnetic angular momentum on the ratio d over a, and that my colleagues have found that rotating TRB Weil superconductor yields a perfect diamagnetism and implies also a way to measure the axion coupling. With this, I thank you for your attention. Thank you.
Please, questions.
Do you think it would be really possible to realize spherical topological insulator? I mean, how to do it? So it should not be possible to cut it from single crystals because you have it is single crystal. You have topological state on the top, and on the bottom you have the counterpart. And it should be grown by this.
This is, I should say that this is a sort of a semi-classical description that utilizes the certain properties of topological insulator on the microscale. So this is a certain rough approximation, of course, of the effect. So I
just for your this system to work, you need the same properties over the whole surface. So if we imagine we try to grow it somehow, it should be grown so as to have the same surface.
Yeah, I understand the assertion. Yeah.
But you have a 3D TI, and we like to think on the top and the bottom, but actually also on the sides, there is the same edge state, right? So also, if you would take, you could do the calculation for a cube as well. The shape does not matter. It's just that the
Topologically equivalent to a sphere. Cube is topologically equivalent.
Exactly. So it would be any finite grain. It should work by any finite grain.
I'm trying to understand how your iteration of rotating superconductor is related to what was done by Fritz London in his book Superfluids, where he considered rotating superconductor and considered that Meissner effect appears due to rotation.
I know about the utilization of this rotating superconductor experiment in Gravity Probe B in 2004, where they used precisely this effect in the to probe geodetic effect. Yeah, so Einstein hypotheses and a frame dragon effect. So yeah, but about what you mentioned,
There you will take mechanically, she's really opposite effect. She creates the rotation. Because there you generate a magnetic field by rotating mechanically the superconductor. Okay, so I would like to discuss something
Okay, let us thank Anastasiia again and all speakers for the session. So we have a coffee break, 30 minutes. I think we can gather at 11:55. No, like 25 minutes.
What's up? Yes.
Yeah, that's kind of your work.
Yeah, I do.
Just this is visible then?
Yes.
Okay.
Okay, so like talk like 25 minutes.
Yes, I always.
It's 20 minutes and I'm just gonna be in.
Okay, good. Thanks.
Okay, hi everyone. So we're trying to be kind of on schedule this time. The first talk we have by Krzysztof Wohlfeld, who's going to talk to us about altermagnetic Polarons.
Thank you very much. Thanks. Can you hear me? Yeah, is it fine? Okay, I'm anyway quite loud. So yeah, so first of all, yeah, really thanks to all the local organizers for putting this workshop together. It's really great to be here, and I think you know, like they said yesterday that they liked us that we traveled here, but this is really zero with respect to what you are doing here in Ukraine and protecting all of us here. So many thanks. So, and of course also, well, the second point is I really thank Jeroen and Sergey for organizing this grant and that we can have, you know, this workshop, well, essentially for free. Yeah? Thanks to the grant from the German ministry. So, okay, so yeah, now does it work? Oh, yeah, it works. Yeah. Okay. Now, well, again, acknowledgements to Jeroen, but anyway, so it's so the talk is basically based on a paper that we published, yeah, I don't know, like a few weeks ago, well, earlier, this year, and which is done together with Maria Daghofer, who was really doing all these calculations mostly, and then Jeroen, who had the concept here, and I just contributed, and I am now presenting it. And so this story is actually, I roughly talked about it, partially introduced this story last year, but very briefly, and I was also online, so I think now I will go much deeper than last time. Yeah, also I talked about several other things last time, so this is kind of a different talk to some extent. But okay, so let me start with the introducing the problem. So where we are. So basically, as you probably most of you know, so ARPES, so the angular resolved photon emission, has established itself as the probe of altermagnetism. You know? And one of the, maybe, I don't know whether, you know, like the nicest example, but one of the most prominent experimental visualizations of this is this spectrum that you see here, which is ARPES on this prototypical altermagnet, where you see actually, can you see this? Yeah, you see. Okay, perfect. Where you see the splitting of the two bands with spin up and spin down, and at particular so-called special altermagnetic momenta. Yeah? And this band splitting, this spin and momentum band splitting, which is observed here, is really large. It's of the order of half EV, and this puts this material in the domain of these strong altermagnets. So this is like on the material side. On the method side, it's like that, you know, this band splitting is really a paradigmatic signature of altermagnetism. Okay, so far so good. Let me now go to what I would like to talk today, which is I would like to actually introduce discuss the so-called strongly coupled altermagnets. So let me firstly tell you what's the difference between the weakly coupled and strongly coupled altermagnets. So, you know, like typically most of the research so far has focused on the weakly correlated altermagnets. Yeah, and the reason for this is that they are, first of all, best for applications, for spintronics, of course, and then they are also, you know, naturally easiest for the ab initio methods, like the DFT or DFT plus U and so on. So these are, of course, you know, very, you know, the two positive points. However, there are also issues here, and one is, of course, you know, as also mentioned earlier today, you know, in finding candidate materials, like there has been, you know, this long discussion on this ruthenium dioxide, and also, you know, like the microscopic mechanism leading to the altermagnetism, you know, in this weakly correlated or especially moderately correlated even more regime, this is not always so easy to determine. Yeah, so it's like understanding magnetism in this itinerant picture from microscopic point of view is not always that clear. Anyway, so, but in any case, because of these two first points, you know, most of the research so far is focused on this. However, one can also think of the altermagnets in the strongly correlated regime, which is naturally not good for applications, because typically these would be then either multi-insulators or bad metals, and they cannot be tackled, of course, in DFT-like approaches, typically at least. However, you know, we have now a larger class of materials that we can explore, because, well, it's another class of materials, well, these strongly correlated altermagnets, and moreover, you know, it's like, surprisingly often, you know, like understanding the microscopic origin of magnetism in multi-insulators or in very correlated regime is often easier than in the weakly correlated regime. So we can understand some features of altermagnetism a bit better here. Okay, so so the main question that I would like to ask in this talk is when we focus just on this class of altermagnets, so these ones where the strong correlations between electrons matter, can we now use ALPers, or rather, what happens if we use ALPers on these materials, on these strongly correlated altermagnets, So will we see such a band splitting as here, or will we see something else, And that's the main question of the talk. Okay. So I will show you some results. I will show you results in the end of the talk. And now I would like to give you kind of a detour, or like some theoretical background, which to most of you, which is behind the study, which I think to most of you is kind of relatively easy, or you know it, but there are also students in the audience, of people coming from other fields. So I would like to use a few minutes, I think probably 5 minutes to a bit more to talk about it. So first of all, just to put us like us on the same ground, or like a starting point, so to maybe some of you who are especially coming not from the correlated community, you would imagine that what ALPers measures is basically like the band structure. And I just took two kind of, let's say, random examples, so just feel not offended that it's like just these two. It's not like that I am specially attached, but anyway, so one is this case where you see a very nice, very good comparison between what the DFT bands and what ALPers measures. This is in an uncorrelated case, and this is actually in a mod insulator, so in a correlated case, but where actually still mean field is enough. So we have a good agreement between what ALPers measures and what DFT plus U not predicts, but what we get from the bands that we get from DFT plus U. I mean, at least that's what the authors claim. I mean, when you look at it, of course, it's one always can have some doubts, but basically that's it. On the qualitative side. Okay. However, like what also like from the very nice talk yesterday by Jörg Fink, what ALPers measures, or by Sergei Borisenko, what ALPers measures is actually the imaginary part of the single particle Green's function. So there's more to this than just measuring band structure. So this is the main object that we have here. And so it's only for the weakly correlated that materials that indeed we have a family liquid scenario, and then DFT or DFT plus U would be okay, and we just see the bands. However, for strongly correlated systems, it's like ALPers is not really the DFT band, and we have to look at this object from the theoretical point of view. Okay, so like cliche example of this, which some of you know probably very well, those who have worked on the cuprates, so which is like this ALPers on the undoped cuprates, which are all of these are like quasi 2D antiferromatic multi-insulators. So that's one of the results already from more than 20 years ago. There are not so many results here because ALPers is difficult on these strongly insulated compounds. But anyway, what you see here, the spectrum essentially consists of 1 or 2 delta-like peaks in the low energy regime, and then there's some part of incoherent spectrum. So this is kind of a qualitative schematics of the spectrum and a particular momentum. And now to understand, to model the spectrum theoretically, of course, what people have been trying to do many years ago, starting with the cuprates, was like, okay, they started with DFT, but of course, this is completely wrong here. We have a good metal in this case, but then one can add U on a mean field level, and this is one of the first results in the 90s on this, and then actually this is not too bad, I would say. So here you see the dots from the ALPer I know, I'm not sure if it's ALPers because there's also inverse photoemission, but anyway, so there's some I think it's probably rather theoretical, just some exact theory, but anyway, this mean fit is not too bad, but nevertheless, there are some questionable assumptions to this, and moreover, Sometimes there are also 2 delta-like peaks here in the upper spectrum. And there's, of course, this incoherent part that mean field will not reproduce. So we are really, we are getting something, but, still, even on the qualitative level, we are not there. Okay, good. So how to explain it? Yeah, and now it's like, now it's like one more important point that I would like to tell you, and then we go back to the altermagnetism. And this is also something that, some slides that some of you have seen from me many times, so I apologize, but to some of you it's something new. So basically, how to understand, what I just showed, this RPS on an 2D antiferromagnet. So basically, in the most simplest theoretical scenario is that or simplest theoretical model is that actually it's a completely different starting point. It's not the band picture, but we start with a 2D antiferromagnet that we just look at 0 temperature, which is ordered, and we just, what RPS does is just kicks out 1 electron. So we say, okay, what happens is we just put a single hole in this 2D antiferromagnet, and we want to understand how this hole moves, and this is really modeling RPS, so or modeling this single particle Green's function, which essentially means kicking out 1 electron and looking how this electron propagates in the ground state of the system, which is here a mod insulating 2-dimensional antiferromagnet. Okay, so we want to understand this, and of course we can do it theoretically, but so the model that we need to solve is actually a Hubbard-like or TJ-like model. So this is the TJ model for those who are familiar with, just to know where we are. And but essentially, it's like it's basically a correlated limit of the Hubbard model. And so what we need to do, kind of with equations, is just calculate the single particle Green's function for this model. However, what I want to tell you now is to get a flavor of what's going on of the physics is that I show you some cartoons so that you see how we look at it, how this, how this hole propagates in such a 2D antiferromagnet. So also it's something that some of you know, but maybe not, probably not all of you. So what happens here is that if we put a single hole in an antiferromagnet, one can use one language with spins and holes, but the other language is that an alternative language is that we talk about magnons and holons. So magnons are excitations of the long gauge ordered antiferromagnet. So this is a holon here. Yeah. And now what happens if this hole propagates, it actually, when the hole moves and exchanges with this spin, the hole moves here, this spin moves here, it actually, this hopping hole overturns a spin, So it creates a defect, in the antiferromagnet, because this spin is down, and since it's an antiferromagnet, these neighboring spins do not like it. In other words, we create an excitation, a magnon. This is a flipped spin, so in real space, it's a magnon in real space, basically. So of course, this costs energy, the spin exchange J, because which is, it's of the order of the spin exchange. These are the bonds which are broken in the antiferromagnet. Okay. Now, but the important point here is that if we continue with the whole hopping, we go to the right, for instance, here, then there's another flipped spin or overturned spin or another magnon in the other language. So this hopping T, which is in the model, in the TJ model, leads now to the to creation of another defect, another magnon, another excitation, which costs another J. So we have another energy cost now of the order of 2. Now it's in total, it's of the order of 2J, of this order of magnitude. It's not exactly this. But what you see here, we realize that the further the hole moves, the more of these magnons are created, of these overturned spins. So the hole move, and so in the end of the day, we can think of the hole being, like in a discrete linear or in the so-called string potential here. So this is almost the whole physics here, though not all, because what is also there is actually the fact that also, there's also some spin dynamics, so some spin flips, or the magnons can annihilate each other. So there are also, so it's not only that the defects are created, but the defects can also be annihilated by the S plus, S minus terms in the Heisenberg Hamiltonian. in the end of the day, what happens, how you should visualize this whole motion is that the whole moves, it creates these magnons, it moves with these magnons, but then these magnons are gradually being annihilated. Yeah, so it moves like we can think of it like the whole slowly moves with these magnons, with this cloud of magnons through the lattice. So this is kind of it very much resembles the thing, you know, the Polaron motion that you know from electron-phonon problem, yeah, that the electron moves by coupling to phonon. So it's kind of similar, and actually mathematically as well, but not fully. So this is all started with, you know, this is a very old story, started in '68 with Daniel Chomsky, Boyarsky, and Nagayev. So then there was a huge hype in the end of the 80s, 90s with the cuprates community. However, you know, there was like a recent revival due to the optical lattice, but not only this, there are also some studies connecting these ideas to the Ancilla-like models by Subesachdev, or there are also still some spin Polaron studies published even last year in PRL. So that's, you know, so it's kind of, despite being so, you know, so old, it's kind of still a relatively active field. Okay. So why this concept is so widely used? So one point is that it really is in the numerics. So this spin Polaron quasi-particle is really, you know, the spectral function is this thing here, what you see. Yeah, it's and actually, this also is visible in more exact numerics in the 2D Hubbard model. So this, you know, this is the spectral function of the 2D Hubbard model. You know, the quasi-particle that you see here is actually, you can see in more analytic results here. And this is this spin Polaron quasi-particle, which moves on a renormalized scale by coupling to these the whole couples to these magnons. So moreover, and this is crucial, you know, this spectral function of the 2D Hubbard model to a large extent qualitatively reproduce also the ARPA spectrum of the 2D cuprates. Yeah? So there's this very good agreement between Hubbard model and ARPAs. Very good, I would say. So good enough, in my opinion. Okay. So this is so far so good. So this is all about the cuprate study. Yeah, so this is how one understands the 2D antiferromagnets strongly coupled. Now we come to the main topic. I think I am almost 20 minutes, but I will just use now, I think I need just 5 minutes or so, which is what happens now if we do the same story, if we repeat the same study, but now not for a 2D antiferromagnet, but for a 2D altermagnet. So what we do here, we take the simplest possible model of simplest possible, I would say, or the simplest possible model on the altermagnet. Of course, another one is the Lviv lattice, but so it's a subjective choice. But nevertheless, we take the checkerboard altermagnet and we calculate the ARPAs, or rather this, I call it ARPAs, but essentially it's just the single particle Green's function for the J1, J2 checkerboard altermagnet. In reality, it's of course not the Heisenberg model that we study here, but rather the TJ-like model, yeah, because we need to model the whole motion here. Anyway, so these are some kind of these quasi-analytic calculations, I would call them, the so-called self-consistent bond approximation, what is done here. And what you see here are the spectra. So this is omega, this is energy, these are momenta, these are the line spectra. And what you see here, this is this single particle Green's function for the spin up. So we kick out spin up electron. Here we kick out spin down, okay? And, you know, like overall, you can see like from far away, it looks kind of similar. Yeah, 5 minutes, good, thanks. But, you know, but the point is that, you know, the difference between left and right is that, you know, that the spectral weight is quite different and these altermagnetic momenta. Yeah? So here you see that this peak has quite a large height, whereas here for spin down and this momentum has very low. The opposite happens for pi half, where this is large spectral weight here, and this is small here. So there's a very strong spin-dependent spectral weight. On the other hand, there's almost no spin-dependent shift in energies. Yeah? So you see the location of these peaks here and here on the left and right is basically almost the same. There are some differences, but quantitatively it's very small. It's a very small effect. Well, and last but not least, okay, maybe I should have mentioned earlier that there are, you see no bands here, just quasi-particle peaks and the incoherent spectrum. Yeah, it's not, it's really a strongly correlated regime. We cannot talk about bands, mean field bands here. And in fact, actually, if we do mean field here, we are really far away. So these are the same, the spectra from before, but now plotted a bit differently. And downstairs here, what you see are the mean field dispersion relations. So they are very different. So it's much worse than for the 2D antiferromagnet. It's really far away. Okay. So this is the main point, actually, of the story. One can also do it on another model. This is a model for this lanthanum vanadate, which is at least for the plane of the lanthanum vanadate, which is an altermagnet because it has antiferromagnetic and alternating orbital ordering. So it's a nice altermagnet, and this is done with some more exact numerics. So this is this variational cluster approximation. You look at these blue parts of the spectrum. This is upper spin up, upper spin down, and you see that basically, for instance, at the 0 pi momentum, you see a lot of spectral weight here, but basically nothing here. So this is also this spin-dependent spectral shift. There are also some shift in energies, but they are much smaller here as well. So this is just the same, but for a different model, roughly speaking. Okay, there's still, I have like 2 minutes? Three. Perfect. So just to give you like still a flavor of what's going on in this cartoonish picture, this is also maybe a bit busy and a bit messy cartoon, which is we have an altermagnet here, a checkerboard lattice, and then we put a hole here initially, and we propagate it from here to here via actually 2 processes. This is a bit similar to the antiferromagnet case, but there are also differences, yeah, and that I would like to highlight here. So first of all, the first point is that when we propagate like by exciting magnons, the difference is that these magnons are altermagnetic magnons. So the hole which couples to these altermagnetic magnons inherits some properties of these altermagnetic magnons. So there is this effect. However, this effect is very small quantitatively. Of course, we can tune some parameters and we can make it a bit larger, but still this is relatively small. But there's another effect which is more important and which is a bit subtle and entangled, which is that, what happens here on this checkerboard lattice, what is possible, and which is not possible on the antiferromagnet typically, which is that, there's this free hole hopping possible across these diagonal bonds, because when the hole hops here, it hops in the same sublattice. So due to this, there's some free hole hopping. However, there are these 2 processes. One is coupling hole hops by coupling to magnons. The other one, the hole hops by, by free hopping. And they come together, but they come together in a non-linear way. It's not like that we add them up. It's just that the hole hops this way, and then, when we will solve the system, it's all entangled here. So as a result of this, what happens in the end of the day is that it turns out that the hole is still strongly coupled to the magnons, and it basically, it moves like in a spin polaronic fashion. So there are no spin-dependent shifts in energies. However, the spectral weight is shifted as a result of the interplay of this free hole motion, and this Polaronic-like motion. So this is kind of a bit subtle and special, but this is what happens here. Okay, so we have a kind of full understanding what all those subtle. Okay, so let me summarize. So this is like the main, to summarize that, instead of, in the strong coupling regime, instead of talking about the spin split bands in ARPAs on altermagnets, we should talk more like about the, spectral weight shift of the quasi-particle peaks. And at the same time, there's almost no shift in energies. Yeah? And also, the mean field is really bad here for the typical models of altermagnets, of course, in the strong coupling regime. So there are also, actually, there's also one other paper on this, not only by us, that I think is still not published, but we went together, so by Michael Klapp. And also, long time ago, we also had some story which was like on a related subject, which basically showed similar spectra, but at the time we were not calling them altermagnets, but it's kind of similar. So that's almost all. I have some postscriptum which I will skip, But I instead of conclusions, I leave you with the same slide actually, like last time. But I think it's the best slide one can have, which is that you know, we are, for those who were not here last time, so an explanation to this picture. This is like our trip more than 20 years ago to Yalta with as a student with the other students, and this is in front of the Lenin monument there in Yalta. And we took this European Union flag that there, and you know, which actually I got in Leiden, but whatever. And you know, we put it there. I mean, these local people didn't like it, but okay. And anyway, and they were looking at us, and I will not tell you what they said to us. But anyway, and but you know, we have also, you know, already from since that time, we have been supporting Ukraine's entry to the EU, and I will be putting this slide till Ukraine is in the European Union. So thanks a lot once again.
Well, thanks for a great talk. I have one comment and one short question here. And the comment is that recently we looked at very related problems in a situation where you also expect strong correlation to be dominant, namely in a one-dimensional parity spin chain with strong interactions. And you ask yourself, what happens to the odd parity band splitting of the electrons that you get in a non-interacting case? And of course, any interaction in one dimension basically blows away the
yes.
You're left with incorrect excitations.
Okay.
And it turns out that if you reformulate the whole thing in bosonization, then the odd parity splitting comes about by a particular backscattering event, 2kF with spin flip, which is irrelevant except at quarter filling.
Okay,
So
interesting.
Exactly the same thing that you're saying, but in a very sort of
yeah, so even more correlated regime probably because it's 1D, so it's fractionless. Okay, thanks. So
magnums in 2 dimensions here. What do you mean?
That's okay because it's 0 temperature.
Oh, it's 0 temperature.
Yes, yeah.
Yeah, I think was want to pass in our sense about the switch to electron instead of a bulk.
Yeah, so if you so basically if you add a single electron, so if you do inverse photoemission, then most of the time okay, so yeah, so here it was the undoped regime. Yeah, when you dope the system, you dope a multi-insulator. Then whether you dope with the electrons or holes, of course, it behaves differently in the second stage. But at the first stage, it's kind of similar whether you dope electron or holes. But now, if you have doping, of course, this is this main question in the cuprate community. What happens if you have a lightly doped cuprate? You have doped holes there, and you are still not in the fermi-liquid regime, and you have this, the pseudo-Gev regime or whatever. So then what happens for an altermagnet? Then it's one more additional complication, I would say.
Yeah, you have different consideration because usually this is called on one side, on both sides it is mod gap, then you have Slater gap. Do you have explanation by itself?
Oh, well, I don't know. It could be, often, whether it's less correlated or more correlated on electron versus hole, it's more like chemistry. Yeah, it's like with a charge transfer in cuprates, or I don't know. Yeah, that's what I would say. But maybe we talk also later. Yeah. That's my understanding.
Thank you for short question. How these results, like for example, on this slide, right? For the systems you studied, ever been compared to DMFT?
No, but you will need, in order to get this, you will need a cluster DMFT.
Yeah, sure.
But if you do cluster DMFT, it should be similar. So there's this paper, you can have a look here. The last paper here from with PRL. This is for the antiferromagnet, not altermagnet. So it's this old story for the cuprates. But there they have this cluster DMFT, and it actually works very well. So this works very well. So just the DMFT approach, which is some approximation, of course, but a very good one. And you compare it with, for instance, with the approach I was presenting here most of the time, they give the same result. Yeah. So.
But yours is vastly more computationally efficient.
Yeah, but it works mostly, for the single hole case. Yeah. And whereas DMFT has other advantages, but yeah, but but this is true. Thanks.
Okay. So let's thank the speaker again. Okay, the next speaker is online, right? So, okay, Olena, can you
I'm
hear
here.
us?
I can hear you. If you allow me to share screen, then I will proceed with my presentation.
I think you can share the screen now.
Okay. So then you see my screen.
Yes.
Okay, perfect.
Okay, wonderful. So the next talk is by Olena Gomonay, and it's on structure, control, and dynamics of altermagnetic textures. So please.
Do you see the presenter screen or normal screen? You see
Presenter screen. Oh yeah, we see presenter screen. Yeah.
Now it's better, yeah?
Yep, wonderful.
Okay. Thanks a lot for invitation. It's my great pleasure to give a talk for the Ukrainian audience, which for people who who have courage to withstand all these things that happens in Ukraine. And my presentation will be also in the line of the conference about the structure, control, and dynamics of the altermagnetic texture. And before I start talking about the physics, I would like to advertise Triple E Magnetic Society, because this year I'm serving as a distinguished lecturer for this society with the lectures about altermagnetism. And this society makes a lot to support the science in Ukraine in particular. So it provides a lot of stipends, and since the beginning of the hot phase, it provides a support for scientists who are working directly in the Ukraine. So if you have a possibility to become a member of this society, you can also have very good discounts or stipends, especially it's important for young people when attending different conferences. But now I would like to switch to the scientific part. And today I will talk about altermagnets, and the main message of my talk is that the altermagnets could be more efficiently manipulated compared to their antiferromagnetic counterparts. And then altermagnetic symmetry allows us to benefit from ferromagnetic-like behavior, even in absence of very small magnetic moments. So, why do we discuss this altermagnetism? I think that today and yesterday it was talked about a lot about the altermagnetism, and we will hear also very interesting talks later. But the altermagnetism as a concept came from the attempts to find more fast, deterministic, low-energy spintronic devices. And of course, our task as a scientist to find which materials are optimal and how can we control and manipulate the magnetic states in the most efficient way. So, spintronics started from ferromagnets, and in ferromagnets we have possibility to write information using spin-orbit talks. We also can read effectively the signals using such effects as anomalous Hall effect. So we have easy reading and writing facilities. However, we are restricted in our dynamics, which falls into gigahertz range, and we are also limited by the density of carriers because of the stray fields produced by the magnetic moments. what is important with ferromagnets, why they were first used for spintronics applications so widely, because they have a quite large magnetization which interacts with the electron spins. And this magnetization induces different effects like spin splitting of electronic bands, which is huge, Faraday effect, which allows us to observe optical effects which depend on the magnetic moments, anomalous Hall effect, and so on. Antiferromagnets. Antiferromagnets came into play in spintronics because they promise a very fast or much faster dynamics compared to ferromagnets, and more dense information coding because of absence of the straight fields. However, the main problem with antiferromagnets is that they are silent. It's very difficult to read and write on these materials, and even as a physicist, we face the challenges of observing and measuring equilibrium states or magnetic states of antiferromagnets directly. So people tried to do different things, looking for some special materials with special symmetry where we can write information using so-called nail talks. But still, everything is yet below the level at which you can face the real technological applications. So no one is perfect, and we need to look for the other materials. So why antiferromagnets themselves are not providing this efficient way of reading and writing? The main reason for this, these are magnetic materials, but they do not show any ferromagnetic-like effect. In other ways, they show no splitting of the band structure, or so to say, the electronic band structure is double degenerate, so we cannot get spin polarized currents simply allowing current flow through the antiferromagnetic textures. Also, all the effects which arise in the magnetic field.
I'm very sorry, like we had a small connection problem with the internet. Could you just start like 1 or 2 slides previously, like 1 minute before? Could you repeat?
Oh yeah, sure.
Thank you very much.
Okay. So these slides, you mean? Or even earlier?
This one? Yeah, this one, yeah, please.
Yeah. So, antiferromagnets, they, though being fast, they couple with the magnetic field very, the coupling with the magnetic field is proportional to the square of the magnetic field. In other ways, all the effects on which we base our spintronic devices in ferromagnets are not allowed or very weak when we come to the antiferromagnetic materials. So the question is whether can we find materials which will combine the benefits of both of ferromagnets with strong response on the magnetic-like effects and fast antiferromagnetic dynamics. The question is, can we do better? And the answer came in 2022 with the work of Libor, Smejkal, Chyzhykhova, and Tomasz Jungwirth, where they introduced this new class of the magnetic materials, which they classified as altermagnets. And again, maybe I repeat this, but I would like to underline that the altermagnets, they show the magnetization-like effects without macroscopic magnetization. And this is the main message of my talk. So in my talk, I will show a couple of the effects which are related with the altermagnetic nature. They behave like ferromagnetic like, but they are not proportional to the magnetization. And altermagnets, the idea of the altermagnets is related with the symmetry classification, which comes from the magnetic environment, from the non-magnetic environment of the magnetic atoms. And this I will explain in a couple of minutes. So, altermagnets, they show strong spin splitting, they show Faraday-like effect, they show anomalous Hall effect, so they are very good for spintronic applications, and we will learn how to do this, how to apply this. So, this is a plan outline of my talk. I will give 2-minute introduction into the altermagnetism and describe altermagnetic order parameter, and then give a couple of examples how we can control the states of the altermagnets using the magnetic field. So here in this slide, you see these 3 types of, or 3 classes of the magnetically ordered materials, which we use today. And I would like to underline that this classification includes not only the magnetic atoms, but also non-magnetic environment. And this is very important, because only if we look at the non-magnetic environment of the magnetic atoms, we can find the difference between antiferromagnets and altermagnets, which shows up in the structure of the bands, electronic band structure. And this type of splitting, alternating splitting of the energy bands, which we observe in altermagnets, can be very useful for the applications. And for example, we can create spin valves. But I will not talk about this, because after the lunch break, you will have a possibility to listen to Felix Casanova, who will explain all these effects in the detail. So I start from introducing the altermagnetic order parameter as a tool for description and analysis of the magnetic properties of altermagnets. And how we do this, usually we distinguish between ferromagnets and antiferromagnets, in old times at least, and we introduced these materials from the point of view of the phenomenological theory as coming from the paramagnetic phase, so non-magnetic atoms. And what is also important here is that all these non-magnetic atoms, which will become magnetic afterwards, have no structure. They could be considered as spheres or points. And then we can color these atoms in a different ways, and coloring gives us an order parameter, either ferromagnetic magnetization or the Néel vector antiferromagnetic order parameter. However, if we take into account also the non-magnetic structure of the crystal, we can imagine another direction of phase transition. We can imagine that each of these spherical atoms is deformed elliptically, and this, or in more complicated way, and this deformation can be either ferromagnetic-like or similar at each magnetic atom, or antiferromagnetic-like, when the ellipses are rotated with respect to each other. And then we can introduce also additional order parameter, which we call altermagnetic order parameter, and then by coloring these deformed atoms, we can get the variety of the magnetic phase. Among those, only one is interesting for us, is its altermagnetic structure. So how to imagine this altermagnetic order parameter and what it will give rise to at the end? For this presentation, I use the example of a rather complicated material, which is considered as a altermagnetic candidate. It's manganese 5 silicon 3. And Helena Reichlova, whose talk will be just after mine, will give more, tell you about different experiments and give more information about the practical applications of this material. I will only introduce, or I will only show how we can introduce this altermagnetic order parameter using this material, and how we can apply this approach for interpretation of the experiments which we have done with it. So I will not go into the details of this material. I will only discuss the fact that the magnetic moments can be localized on certain manganese atoms. But each of the magnetic atom has environment created by non-magnetic silicon and manganese 3+. And what we can do for introducing the altermagnetic order parameter, we take first the magnetic moment which belongs to one of the magnetic sublattice, and then we look at the environment of this atom and construct a certain tensor. This, in the simplest way, this tensor can be considered as averaged XX, YY, and so on components which are constructed from the vectors which connect the magnetic atoms with non-magnetic neighbors. In this way, we construct a certain tensor which has a symmetry, which has a structure which depends on the symmetry of local environment. And then what we can further do, we can do exactly the same procedure for the second magnetic atom belonging to the other magnetic sublattices. And the altermagnetic order parameter is the difference between these two, because this is exactly which shows how so this combination behaves very similar to the behavior of the Néel vector, which is order parameter of the magnetic order. So this is the order parameter. What we can do and why should we apply so complicated procedures to describe our systems? Using this altermagnetic order parameter, we can construct the effective potential of the energy, of the magnetic energy of the system. And what is important, this order parameter is an indicator of the terms which appear in the altermagnetic phase and are zero in the antiferromagnetic ordering. And we are looking for the terms which are altermagnetic and also are combinations of the magnetic vectors and the Néel vectors M. Why? Because these particular terms show how our system couples with the external magnetic field, and also they show how the energy of the anisotropic energy of the magnetic system can be controlled and influenced by the magnetic field. So for this particular material, we calculated the energy landscape in presence of the magnetic field, and what you see now in the picture is a energy landscape in the coordinates, spherical coordinates of the Néel vector, and the blue dark color corresponds to the energy minima. So depending on the direction of the magnetic field, we can see that the energy landscape changes, and it favors different directions of the Néel vector, as shown by the arrows. So, in such an altermagnet, by applying magnetic field, we are able to change the orientation of the Néel vector. It's not surprising, it was known for a long time. But what can we learn from this, and how can we apply it to the real experiments? And the main tool to study the structure of the altermagnets, especially these thin film samples, is measuring ferromagnetic-like effects. And one of the very important ferromagnetic-like effect is a Hall resistivity. So the idea of the experiment is very simple. We apply current in a certain direction, and we measure resistivity is in a perpendicular direction to the current, and presence of the external magnetic field. And the role of the magnetic field is to change the magnetic structure, so we can probe different orientations of the Néel vector, and from the behavior of the anomalous Hall signal, we can then reconstruct the structure, the magnetic structure of the sample. Everything seems nice and good, but the problem is that this anomalous Hall resistivity is a kind of projection of the magnetic properties to the certain plane, so to say. And then from this projection, we need to reconstruct the whole structure. And to do this, what is also important, what can help us, we need to know how the anomalous Hall effect is related with the magnetic structure. And for this, we use again this phenomenological theory with the altermagnetic order parameter, because the symmetry considerations allow us to construct the expressions for the anomalous Hall response as a functions of the certain components of the Néel vector and magnetization. And you can see that the contribution which depends of the Néel vector components is related with the altermagnetic order parameter. So it's directly altermagnetic effects. Now, how we can use it? So here you see the example which refers to the manganese 5 silicon 3 sample, where we measured anomalous Hall response of the system depending on the orientation of the magnetic field. And magnetic field was rotated from horizontal to vertical axis through 360 degrees in different planes, as shown here, here, and here. So by taking these angular dependencies, we first find out a very different behavior and very strange behavior depending on the orientation of the plane in which the magnetic field was rotated with respect to the crystallographic axis. And then we tried somehow to reconstruct the magnetic structure. And for us, there were two smoking guns which allowed us to find a relation between the response and the structure which we assumed. And these two smoking guns was this dependence, which has definitely two states, in contrast to the others which have like 4 different states, and also this dependence in which we observed very strange, like web-like or powder-like dependence, where they observed a negative slope of in the certain range of the angles. And here, by using our assumption about the anomalous Hall effect, we were able to separate dependencies of the Néel vector and magnetization and their contribution to the anomalous Hall effect. So for one geometry, you see that the Néel vector swap 180 degree, and this is in very good correspondence to what we see in the experiment. And even more exciting is this spider-like dependence, where the dependence of the Néel vector versus angle is very different from what you get from the magnetization. So then from a comparison of the experiment and theory, we concluded that the contribution of the Néel vector to the outcoming signal is very strong and dominating. And this also tells us that in case of the altermagnets, the ferromagnetic-like effects can appear simply from the Néel vector, strong magnetic order parameter, and they shouldn't be proportional to the direct value of magnetization. So in this way, we reconstructed the structure. It was nice and good. And I would like, at the end of my talk, I would like to give another example where we use the same strategy and got very similar results. It's a chromium antimony, which is also an altermagnet, which can be also very useful for application because it's a metal. And in this case, we can introduce the altermagnetic order parameter, which is much more complicated. So it's a third rank tensor, but we do it following the same procedure. And again, using this altermagnetic order parameter modeling, we are able to reconstruct the structure, the magnetic structure of chromium antimony. And here I would show only a couple of slides. So here you see anomalous Hall effect measured for this material. And of course, there are a lot of lines which are quite complicated. But the main thing which surprised us when we have seen these dependencies is that we see two hysteresis loops. The horizontal line is the magnetic field, and these loops show a very strange behavior in the sense that for the positive values of the magnetic field, we observe like positive contribution to the anomalous Hall effect and negative contribution to the anomalous Hall effect. In ferromagnets, the sign of the anomalous Hall response always correlates with the sign of the magnetic field. So even looking at this experimental dependence, we can conclude that in altermagnets, the behavior of the ferromagnetic-like variable, anomalous Hall effect, is influenced by some other contribution that magnetization itself. So we also followed the same strategy. We modeled the magnetic energy using our technique, and then what we found out that the system has many phases, much more than manganese by silicon 3. And when we travel along the magnetic field, we can jump from one state to the other. And this what we found out when we start looking at the magnetic signals attentively. So we splitted the whole response into two parts, magnetic part and the Néel vector, and we found out that the magnetic part behaves monotonously, as it should be in the magnetic field for every ferromagnet, but the contribution coming from the Néel vector is non-monotonous, and this is exactly what gives us a non-trivial dependence of the whole signal and these two types of the contribution with opposite sign. With this, I am at the end of my talk, and the conclusion is that altermagnets show strong ferromagnetic-like features which are not related to the magnetization. So everything which is not forbidden is allowed. And with this, I would like to show people who contributed to this work and much more. We also collaborated with Felix and Helena and others, but they will show their results by themselves. And thank you for your attention.
Thank you, Olena. Thank you for a very nice talk. So questions? Yes, Sergey.
I'm confused by that in your slides, anomalous pole resistance was like a scalar quantity. So how the setup of experiment looks like? In which directions you apply current? Is all the time, for example, you consider plane perpendicular to magnetic field? How the setup looks like?
Thank you for your question. I skipped this. Of course, we measured, of course, the anomalous hole is the tensor quantity. And here you can see the scheme of the experiment which was applied for manganese 5 silicon 3. So it's a whole bar which is on top of the film, and we are able to measure the resistivity, the voltage in certain direction. So we are sensitive to the whole resistivity along z-axis of the film. In this case, it is 0001 direction, crystallographic direction of the crystal. In case of the chromium antimony, the geometry was more complicated. I did not went into these details, but it's shown here. So the material was grown on the film so that the hexagonal axis was parallel to the film plane, and again the whole signal was measured. So the whole resistivity corresponded to this component, out of plane component.
Other questions? Okay, I have a very naive question. Like when you think about your altermagnets, what is the phase structure there? Is it just altermagnet to paramagnet transition, or what's the behavior? Because you mentioned the order parameter, like how does it behave? How does it change?
It's also a good question. I can give an example of martensites, magnetic martensites. So these are materials which undergo two types of transitions, magnetic transition and structural transition. And depending on which alloy you are considering, you can have different, you can have first magnetic transitions and structural, or vice versa, or two transitions almost at the same temperature. So in my view, these altermagnetic transitions or altermagnetic materials could be considered in a similar way. For example, I can imagine cuprates with the octahedra, which are all aligned in the same direction. And then if at some temperature or due to some stress or whatever, these octahedra can rotate in different directions. In this way, they create altermagnetic phase. But it's not altermagnetic before the magnetic ordering. Yeah, so such type of the transitions could exist and could be induced chemically. On the other hand, I can also imagine that this phase from which we get altermagnetic phase does not exist at all. Yeah, we can use it simply as a technical tool to define different contribution into the energies.
Okay, thank you very much. Okay, with this, let's thank the speaker again. And move to Helena Reichlova.
Hello, hi, can you hear me?
Hi, yes.
Hi, perfect. So let me try to share the presentation. So now you have to help me to tell me if you see the...
Or it's loading. Yeah, we can see it.
you can see it in the present remote and the resolution is sufficient, or should I still try to adjust it somehow?
Yeah, it's wonderful.
It's wonderful.
Yep.
Perfect. So
Yeah,
everything
okay.
is perfect.
So-
Set. So yeah, go ahead.
So the next speaker is Helena Reichlova, who's going to talk about magneto-thermal transport experiments in Altermagnet, and the floor is yours.
Thank you. Thank you for the introduction and thank you for the invitation. I'm always honored to talk here, and also it helps me a lot to get overview of the research in Ukraine and where our shared research interest and how we can build on it. So thank you for more invitation. So today I will try to say something about a little bit not only altermagnets, but more focused on the general magneto-thermal electronic transport. And then I will show some experimental results in altermagnetic materials, in particular the mangan 5 and mangan telluride. As an experimentalist, I naturally work in a broad collaboration. You see here like one of our, let's say, department retreat with our close collaborators. We are many people, and here you see also a lot of familiar names, a lot of colleagues from IFW Dresden, Olena and Mainz team gave us like very strong support, and also Felix, who will talk after me, and a couple more colleagues from France and from Germany. So to introduce generally the thermoelectrics, I just put it to context of cross effects. There is many cross effects where we link like some different properties, and there are different transport properties, heat, electric, diffusion, right? So these are all well-known phenomena. And here, this talk, I will focus in particular to the cross-coupling effects between the heat and electric properties of the material. And when we focus on this, particularly the heat and charge transport, right, then we can link them by such a formula where we have charge transport, we have some heat transport, and they are somehow proportional to the electromotive forces, which make the transport happen, the electric field or the thermal gradient. And now the proportionality is described by these coefficients, and these are all tensors. These are our well-known conductivity, or the alpha, which we know, the thermal conductivity of a material. And these tensors, they have naturally some diagonal and off-diagonal components. Then by multiplying it with the electromotive force, right, we get all the corresponding elements of the current. And what is important of these tensors is that they have time reversal odd and time reversal even component, right? So the time reversal odd we define as the difference between the sigma and time reversal reversed divided by 2. This is the sum divided by 2. And when we focused on this time reversal odd phenomena, then we can ask how to break the time reversal symmetry, right? How to achieve that these two kind of sigma are not the same. And this brings me to like a very simplified cartoon, but the time reversal symmetry can be broken by external magnetic field naturally. Then we talk about ordinary effects, well-known ordinary Hall effect, and the thermoelectric counterpart, the Nernst effect. And then this is not the only way how we can break the time reversal symmetry, and we discussed it a lot already during this workshop, right? The magnetic materials, they break this naturally by some magnetic ordering, and then I will refer to it as an anomalous effect, anomalous Nernst effect, or anomalous Hall effect. And the key thing here, and I will mention it once more during my talk, is that we then don't rely on the external magnetic field. It's the magnetic order parameter of the material itself, which dictates the presence or absence of these anomalous phenomena. And importantly, they can also exhibit spontaneous present in zero magnetic field, which can exhibit hysteresis. Basically, the two states are not identical, are not equivalent in the zero magnetic field. So, and now before I go to some actual experiment. Let me just give a brief motivation that it's not only academic curiosity, right, to study these thermoelectric effects. There is already a wide range of application of the thermoelectric elements, especially the Seebeck type module, right? This is a well-known thing used pretty widely. But most typically these Seebeck modules, they rely on this phenomena where the thermal gradient, we look at the voltage which is generated along the thermal gradient. This is this, let's say, longitudinal component, diagonal component of these matrices. And the Nernst type module is like far less utilized, and despite it would be obviously advantageous, right? So it's more simple, it would be more flexible. We can then, once we consider the symmetry, right, we don't need two elements, we can have only one element. And we can also think about geometry, because here the voltage is suddenly generated perpendicular to our driving force, the thermal gradient. We can also imagine to wrap by some sort of blanket, some source of heat, and it will generate a voltage for us for some heat harvesting. It would be very efficient. And next to that, we also have shown that this can be used also as an elegant magnetic microscopy tool. So all these things kind of seem to bring Nernst like a very interesting also for application perspective. However, you probably know that the efficiency of these transversal effects is generally like lower, and the efficiency is the main roadblock from wider for wider application or wider use of this Nernst or anomalous Nernst effect. So before I go to the magnetic systems, let me also mention that there is very active area of research also towards improving the Nernst efficiency in non-magnetic materials. And here again, staying in this semi-classical picture, there are two ingredients which we want from our materials to go towards a high Nernst effect. And one of them is naturally to increase the mobility. With higher mobility, we will also have a higher Nernst effect. And also to look for materials which avoid Sondheimer cancellation, which basically says that in materials where we have a single electronic band, the Nernst effect almost cancels with this whole, because we generate also by the Seebeck effect transversal field, which is then canceling our Nernst effect generated electron motion. So we look for materials where we have both electrons and holes, so that they can act constructively and they can lead to enhanced Nernst effects. So with these two ingredients, you already see probably that this is also one of the motivation for this extensive research of topological materials for thermoelectronics. There is a lot of exciting results. And this simply comes also to the fact that with these topological materials, right, we have this linear dispersion, which naturally gives us the high mobility. We have also relatively rich band structures, which have both electronic and whole carriers, so that we kind of can get exactly this complex band structure, which is in favor of enhanced anomalous or ordinary Nernst effect. And in particular, with this tungsten ditelluride, it was shown that it can be like very large. And also we, with IFW colleagues, we looked at this family of materials which are isostructural to the tungsten ditelluride more systematically, and we shown that this is indeed present in this full family of materials. So it's not some outlier, it's really the direction, these materials which are very promising for enhancement of the Nernst effect. So this was to the non-magnetic materials, but now let's move to the magnetic materials, and this is where the time reversal symmetry is broken by the magnetic order itself in the material. And we know, right, that in these anomalous phenomena, we have this intrinsic and extrinsic contribution, and this intrinsic origin of these phenomena is indeed linked to the electronic bands, and this does not need to scale with the net magnetization. This is already established in the field. It can be present in antiferromagnets, in other compensated systems. It's linked to the Berry curvature, and it was observed already in many compensated magnets, generally the anomalous Nernst effect. So from that perspective, it resembles the anomalous Hall effect, which might be the better known phenomena. And the anomalous Hall effect has this Onsager relation, right, which tells us something about the symmetry of the tensor, and the anomalous Hall conductivity is the antisymmetric tensor. It's the antisymmetric part. And how is the anomalous Nernst effect? Yes, well, the most typical answer which we get is yes, they are somehow linked via something which is called Mott formula, Mott rule, which enforces the same symmetry naturally because it's just somehow proportional. The anomalous Nernst conductivity is somehow proportional to the anomalous Hall conductivity. So by this Mott formula, we very often enforce the same symmetry on the effect, and this is how it's very often seen. And I will then, at the end of my talk, discuss how this is valid and if we can go beyond. So now I kind of established that anomalous Nernst effect is kind of present if the anomalous Hall effect is present, right? So let's now also discuss how large it is. Is there some way that we can enhance the anomalous Nernst effect also in some materials, like for example, altermagnets? Because as I said on the beginning, the small efficiency, the small magnitude of the anomalous Nernst coefficients is one of the roadblocks. And here I come back to the mangan 5 silicon 3, which Olena so kindly introduced. And as Olena already mentioned, it's when it's in this thin film form with this hexagonal structure, it's an altermagnet, right? And what we also know that it's a metallic thin film, which shows the anomalous Hall effect with a particular anisotropy, as Olena discussed. But for purpose of my talk, let me just kind of summarize that yes, indeed, it has an anomalous Hall effect. It has a spontaneous signal, so it's present in zero magnetic field, and it's absent above the Néel temperature, which is around 240 Kelvin. And indeed, the magnetization is small, vanishingly small, mostly below our detection limit with the conventional magnetometry. So these are our mangan 5 silicon 3 films. And despite being thin films, despite being metallic, when we put them into our anomalous Nernst experimental setup, where we put like a good heat bath on one end and a heat insulator on the other end, and we kind of generate heat locally, and then it develops a constant thermal gradient in our full chip. So then when we put it to such an experimental setup, we see that we can clearly observe anomalous Nernst effect. These are the yellow points here, which is spontaneous. This means present in zero magnetic field, and in a large extent it copies the symmetry of the anomalous Hall effect, exactly as one would expect from what I've told you before. So it seems that in this material we have anomalous Nernst effect present. It has the same symmetry as anomalous Hall effect. And let's now look at the magnitude, right? So we plot here all the materials which you can find, or a lot of materials which you can find in literature where the anomalous Nernst effect was reported. And we plot all antiferromagnets, ferromagnets. We kind of don't make any distinction. And we, on this axis, separated by the net magnetization. And here we put the magnitude of the Nernst effect. And the values which we measure in our mangan 5 silicon 3 films, they are, I would say, comparable to many of other compounds which were reported. So you see that we have, of course, some outliers here. We have the spectacularly efficient material, but based on uranium, based on a heavy element. Then we have some of these very nice works on these topological materials, which I also mentioned, that in these materials it is enhanced by this presence of these Weyl cones. But our system, despite being thin film, metallic, lightweight elements, it's kind of not completely like zero compared to these systems. And this was for us already to certain way surprising, because we also know many other materials which were metallic, and for example, here we measured like very small Nernst effect. So here it's definitely something which we thought that it's special. And then we talked to our colleagues in Mainz, particularly Varley Campos did amazing work. And here I show you his calculation of momentum resolved anomalous Nernst conductivity. And he shows here the hotspots of the Berry curvature, which kind of gives the value of the anomalous Nernst conductivity. First interesting thing is that here no contribution from these Weyl points. So there are no Weyl points close to the Fermi level which would be contributing here. Instead, there are these altermagnetic pseudonoodle surfaces and ladder transition between the altermagnetic split bands, which both of them rely on the fact that, again, we have this altermagnetic splitting between the bands, which then gives rise to this non-vanishing Berry curvature. And the fact that these kind of features are present, we think is a good hint that this might be turning knob to again find more materials where the anomalous Nernst effect will be efficient, exactly because of this altermagnetic splitting. So this was anomalous Nernst effect in the mangan 5 silicon 3. And now I just want to go to the last part, which I mentioned before. And that's something a little bit more complicated, but I think even more interesting. And just like it's not somehow only for altermagnets. I think this is something which is general. I just will show you later on one of the altermagnets, but this is applicable, I think, to relatively broad range of materials. And I said this mod rule, right? So it's already since like ages, also two gentlemen from actually our institute in Prague, they did great work there, showing that the mod rule holds only for non-interacting electrons, elastic scattering. It's actually in very, let's say, ideal case. But the violation of mod rule is kind of actually relatively common. And it was also reported in, for example, here some theory work from Jonathan Nocky in Dresden. We also observed it in some kind of fluctuations around the phase transition. So the mod rule can be in principle violated, or experimentally it's definitely reported that the Hall and Nernst do not need to have the same symmetry. And when we look at it from some more fundamental symmetry arguments, then I show this Onsager relation, right, for the anomalous Hall effect, that it is enforced to be antisymmetric. However, because the anomalous Nernst effect here is linking like slightly different phenomena, right? It's linking the charge transport to some thermal gradient driving force, and the inverse beta effect, which is the sort of the second tensor in this matrix which I was showing, they don't necessarily need to be the same, right? And therefore, the anomalous Nernst effect does not necessarily need to be antisymmetric. And indeed, when one then starts to look on some concrete material systems, these two, there are many pretty common crystals where the symmetry of the anomalous Hall and anomalous Nernst effect does not need to be same. Generally, like the anomalous Nernst effect symmetry requirements are simply lower. And one of these crystals, which you see that it's not very exotic, is our well-known mangan telluride. It was also mentioned during this workshop, but just to remind you, this is an altermagnetic semiconductor where the manganese is forming these hexagonal planes, and the tellurium cages around break the rotational symmetry. Therefore, it's having this altermagnetic properties. But what is here important to recall is that the anomalous Hall effect, the spontaneous anomalous Hall effect, which was reported, is kind of assuming the spins along the A minus 30 degrees crystal direction. So when I look at my A and B here, then the spins point toward in the plane, in the AB plane, but along the direction A plus 30 degrees. And if the spins were along the A direction, the anomalous Hall effect is not allowed. This is simply, yes, as it is. And it's quite different to the anomalous Nernst effect, because if you do exactly the same analysis for the anomalous Nernst effect, the anomalous Nernst effect is allowed for all in-plane Nel vector direction. So it's along the A minus 30, A asterisk sometimes. So it's along all the spins in the AB plane. And yes, here I show like this analysis from Jakub Železný, from our great colleague here at Prague. And this is the well-known matrix, right, for the anomalous Hall effect, where we expect it in this transversal direction in the AB plane. Here, this assumes the spins along the A plus 30 degrees. And the same when this is the anomalous Hall conductivity and this is the anomalous Nernst conductivity, you see that it's allowed basically in all the AB plane, and it's even allowed along the longitudinal direction. So when I now try to make like a cartoon-like summary of Jakub's analysis, then we can think about the two cases, right? One of the proposed easy axis is the spins along A plus 30 degrees, and there we get these effects allowed for the anomalous Nernst effect, and these kind of components allowed for the anomalous Hall effect. And once the spins are along the A-axis, nothing is allowed for the anomalous Hall effect. However, the anomalous Nernst effect is still allowed. So having this in mind, let's just look into the experiment. And here we focused on high quality single crystals. They were prepared by Klára Uhlířová, our colleagues from Prague, and they are having like a good structural properties. These are actually the samples where also the ARPES results were reported. And why we like the single crystals here, because we can form freestanding samples. Once we work with thermal gradients, right, it's always good to do not have any heat sinks where the heat can go. So we have a freestanding crystals where there is a heat, and then the full heat is kind of propagating through our crystal, and then we can put our contacts into the various directions to measure along different crystal direction. So these same crystals, when they are bulked, right, we can also very nicely measure them in magnetometry, and we can show that it has this kind of textbook antiferromagnetic behavior, right, when the susceptibility, when it's measured perpendicular to the spins or parallel to the spins, has a different temperature dependency, and the overall net magnetic moment is vanishing. So let's just look on the transport directly. So now we connect our contacts and we measure the anomalous Nernst effect in the standard geometry, that we send the thermal gradient along the B direction, we detect along the A direction and apply the magnetic field along the C. So this is how the raw data look after taking the symmetric and antisymmetric part. We see that we can observe a clear spontaneous anomalous Nernst effect, which is vanishing above the null temperature. But now when we kind of look back to the table, which I showed you before, so we also can measure along the B direction, right? So we keep the thermal gradient still along the B direction, but now we also measure the voltage along the B direction. So in some sense, longitudinal geometry. And also in this geometry, we can see a clear spontaneous effect, and the effect is vanishing when we put the contacts along the C direction, along the out-of-plane direction. And in the same crystal, we can also measure the anomalous Hall effect, and you see that the anomalous Hall effect is kind of clearly very different. There is most striking thing that there is no hysteresis open. There is nothing like in the zero magnetic field. This is the region where we focused on. There is simply no anomalous Hall effect observed, and also not on the longitudinal contacts. These data are very noisy. So what we think is the reason for that, that we indeed have an anomalous Hall effect and anomalous Nernst effect, which are different in the system. And we think that it's fully consistent with the easy axis direction along the A, not along the A minus 30, so that we have the arrangement where the anomalous Hall effect in zero magnetic field is not allowed. However, the anomalous Nernst effect is still allowed. And how is this consistent with more kind of reports and so on? So first, it's important to say that in the single crystal of mangan telluride, there is a large scatter between samples. This is not observed only by us, but also many other groups, that it seems to be like relatively narrow choice of samples of the single crystals which do show the anomalous Hall effect. And this might be exactly because the easy axis sometimes is along A, sometimes along A plus 30. But also from our measurements, what we observed that when we measure anisotropic magnetic resistance in thin films, you see that it shows this kind of characteristic hexagonal symmetry. And in some of the maxima and minima, you see that it's getting more sharp or more, let's say, shallow, which again points like towards what is the easy axis, what is the hard axis, right? Because if you have something more pointy, this is more hard axis. If you have something more shallow, it's like somehow more easy axis. And there is a clear distinction, and it seems that the A plus 30 degrees is the easier direction in the thin films, consistent with what is reported for the thin films. However, nothing like that is present in bulk, so either they are equally easy or the A is easier. And last thing, when we measure the magnetometry very carefully in the single crystals, then when we measure the susceptibility for the A, this is the A direction, and this is the A asterisk is sometimes labeled like a minus 30. So you see that the A looks also like an easier axis from the susceptibility measurement. Last thing which I want to mention is that also our colleagues, they did like muon spectroscopy, and they again in single crystal have suspicion that there is some reorientation of the easy axis from A to A prime. So all that points us to the consistency, that we think that the easy axis along the A direction is kind of fully possible in the single crystals, and this is also what we think explains our discrepancy between the anomalous Hall and anomalous Nernst effect in our mangan telluride crystals. So I think this brings me to the conclusion. Of course, big thank to our group. Here are 3 papers where I think which I talked about are published or will be published. And I kind of introduced the anomalous Nernst effect as a useful phenomenon, not only from the basic understanding, but also for application. And in many of these kind of topological materials, I think it's a very exciting area of research, and enhancement of the Nernst effect was achieved. I also discussed that the symmetry between the Hall and Nernst does not need to be the same, and I illustrated on 2 cases of altermagnetic materials, which is in the center of our research. I showed in the mangan 5 silicon 3 that indeed the symmetry of the Hall and Nernst is the same, and that the magnitude of our measurement is comparable to the other magnetic systems. And in the mangan telluride, we have the anomalous Hall and anomalous Nernst showing different symmetry, and we think that it's consistent with having the easy axis along the A direction, which would then allow for different symmetry, for lower symmetry restrictions on the anomalous Nernst effect, and compared to the anomalous Hall effect. So thank you for your attention, and yes, happy to answer questions.
Thank you for a very nice talk. We have questions. Yes.
Yes, thank you for the nice talk. I have a question about your tensor for the anomalous Nernst effect. Because if I understand correctly, there were parts. Yeah, the part that distinguishes the anomalous Hall effect and anomalous Nernst effect is even in time reversal. So it's a symmetric part of the tensor. Can you comment on that?
Sorry, so you refer to this one or to?
Yes, you have that XY matrix element. You have minus X1 sine phi, and Y-axis also minus X1 sine.
Okay, so this must be different slide, right? This was somewhere here.
No. It's on that slide that you were showing.
Okay, but this is
the orthogonal element has a symmetric part and anti-symmetric part in your alpha.
Yeah, sure. Okay, so the alpha has also the diagonal elements non-zero. Yes, exactly. But they are kind of odd under reversal of magnetic field, right? So this is now a little bit like a question of definition. So you have really Yeah, this is exactly the point, right? That you can have components which are having the Nernst like the odd effect on the diagonal components, because the Nernst effect has the lower restrictions on this kind of conductivity, on the anomalous Nernst conductivity. Okay, so yeah, okay.
Thank you for very interesting, inspiring talk. I would like to understand kind of from general physical consideration, what are the reasons when anomalous Nernst effect does not follow anomalous Hall effect? What happens to the system?
This is, I think, very, very good question, and this is like something also we discuss with many colleagues. There are, of course, multiple mechanisms, right? I listed some of them. Some of them simply in the Nernst effect, you have also contributions from magnons, right? From some kind of drag of magnon drags and all these things. You have some fluctuations, right? So you kind of at the phase transition, you increase the entropy, and then it kind of also translates into the Nernst signal. So they are a little bit microscopic origins which can contribute, which are then not contributing to the anomalous Hall. And the Mott formula, right? The Mott rule. This is limited to these electronic contributions of non-interacting electrons, like relatively simple picture, which in the real materials is not always fulfilled. Did it answer the question or not?
Thank you. Sergei says, thank you, Helena. Thank you for your talk, which I enjoyed very much. And I'm the third theorist now that's going to ask about the same point. So it's obviously kind of counterintuitive. So does it follow from the spin group analysis per se? I mean, if you look, does it follow from that without any thinking?
Exactly. So it's just to take the symmetry, do some kind of rotations, right? So here I should really give the main credit to Jakub. This is Jakub Železný who does kind of all this putting in the matrices and doing all the rotation and putting it in. But exactly, this is saying nothing about the magnitude, saying nothing about if it's kind of large or small or but it just says that it's simply allowed to be present, that the restrictions which we have for the anomalous Hall, that sometimes simply when the spins are along A, right, it cannot be. But then when you kind of do the same matrix, which tells you that the anomalous Hall conductivity is kind of 0 for the A along A, when you do the same for the Nernst, it's kind of giving you these terms, right?
Okay, yeah, so thank you. And my question would be also if the nil vector is along the Z, so like in chromium and timonite.
Z direction. This will not. I would need to check, but I think this will not allow anything. So this will be forbidden also.
Sigma is not allowed, and you say alpha is also not. Sigma is 0 by symmetry, and then alpha also 0 by symmetry in that case.
Sorry, can you say once more the question?
So if you have chromium and timonite and then the orientation along the z-axis, then we know that sigma is 0.
Yes.
All tensor
Yes.
are 0. And
Yes.
we're also saying the all tensor elements of alpha likely are also 0.
Yes. I think yes. I'm almost sure that yes. I think that also in chromium antimony you would need to get some projection to the in plane with the we would need to kind of torture it somehow a little bit to the in plane to get the anomalous Nernst effect. Spontaneous in the zero magnetic field.
Yes.
Okay, so I think we've finished the session today. Let's thank the speaker again.
Thank you.
Now we go for lunch and reconvene. Well, we are 30 minutes behind the schedule, so do we start later or do we?
It depends on the next session, but I know they're all online.
Yeah, they're all online. Felix, are you there? You're the next speaker after lunch. Yeah, would it be fine if we begin?
We can go later. I mean,
Yeah,
I'm
let's
one
start.
hour behind, so I will not go for lunch yet.
Sorry, again?
15 minutes.
Yeah, let's start your talk at 13:15. Your time.
Yeah,
If
yeah,
it works.
okay. So 15 minutes later than
Yes.
scheduled.
Yes. Thank you.
Okay, perfect. I mean, okay, and there are two more speakers after me, so I hope they will also be fine with this.
Yeah, I'm okay with that, yeah.
Great.
Good. So we meet at 1:15. No, sorry,
Yeah,
12:15 for
1:15.
you. Yeah.
Well,
No,
1:15
2:15
for
for you.
you, 2:15 for us. Yes.
Yes, yes,
Great.
yes. Okay, good. See you later. I guess people still are having lunch.
Yeah, people are arriving back now. You can hear me?
Okay, good. Yes, yes.
Yeah, we also hear you. So I think we are, give it a couple of minutes and I think we can start. I think you're muted, so we don't hear you. Yeah.
Yes, important point. Okay, thanks
Yeah, now we hear you. Go ahead.
for introduction. I hope you had a good lunch. It's a pleasure to be in this workshop, even if it's online from my side. And what I wanted to talk today, here is the title, right? It's experimental observation of a spin injection in an altermagnet. We've heard several talks already that in altermagnet we have this alternating spin splitting. That's where the name comes from, right? And one of the most obvious applications in spintronics is that it means that the current has to be spin polarized and then you can have a spin injection, right? But this experimentally has not been unequivocally observed. So, and the work I want to present here is a very clear observation, experimental observation, that this is possible, right? So because of this, I will first give a general introduction of the concept of spin injection, which is very important in spintronics, and see how, because of the property of altermagnets, it should also be possible to do in altermagnets. And finally, in the third part.
Sorry, Felix. I think we are seeing your PowerPoint application, not the presentation. So we're still seeing the first page.
What about now?
Yeah, now it's full screen. Yeah.
Okay, maybe it was an issue with the whatever the mode we're using. Okay, so now you see my outline.
Yeah.
Good. Okay, so I will start with introduction of to spin injection, right? I mean, in spintronics, one of the driving forces now is to use pure spin current in the devices, right? That's one of the basic stuff in spintronics. One motivation is to be able to integrate memory in the form of magnetic elements and logic operations by passing current through these magnetic elements. So the information is taken out of it in form of a spin current, and then using these spin currents to perform logic. This integration would increase the speed and will decrease the power operation. And indeed, in the last years, there's been different spin-based logic proposals. For instance, this magnetologic gate by Andriy and this all-spin logic by Bain and co-workers, with this common idea that you have a small ferromagnet, a nanomagnet, where the information is stored, right, magnetization up or down, and then by passing a current through it, by doing a spin injection, the information is injected into a non-magnetic channel, and then all these spin currents diffuse and mix, and then you make the operation, right? Also, more recently, Intel has proposed this magnetoelectric spin orbit logic, where again the information is stored in magnetic elements, and you pass a current to convert or to pass this magnetic information into the polarization of the spin currents, and then you read it out by, in this case, the inverse spin Hall effect, right? So in general, if we don't care about the spin, we know just the charge. You define the current is all spins up and spin down in the same direction. That's how electronics works. But if you take into account the spin of the electron and you define current for spin up and spin down, if this current is different, basically you have a net flow of a spin angular momentum. And this is what spintronics exploits, right? So in other words, if you pass a current in a normal metal, this current only has charge and it's not spin polarized. It doesn't have any spin current flow. But in a ferromagnetic material, because the conductivity for spins up and down are different, the current has, a net charge current flowing, but also a net spin current flowing. That's what we typically call a spin polarized current. But there is even the option that you can have that all your spins up are flowing in one direction and spins down flow in the opposite direction. This way you can have a net charge current, which is 0, but you still have a net spin current. So the angular momentum flows in one direction, right? So that's what we call it pure spin currents. And this is very interesting to use. But you need typically to do some engineering of devices, right? In particular, if we want to create these pure spin currents in non-magnetic materials, you always combine or typically combine a ferromagnetic material as the spin source and a non-magnetic material. There are different strategies. I would just explain one, which is probably the most important one for applications of spintronics, which is electrical spin injection. I will explain this in a minute. But there is also another way to generate pure spin current, which is very interesting and important in spintronics nowadays, which is the spin Hall effect. In this case, you don't need the material to be magnetic at all. You only need spin orbit coupling. And this also creates transverse spin currents. And I will explain more in detail in a minute. Right. So the basic concept of electrical spin injection is that in a ferromagnetic material, due to the exchange coupling, the density of states of spin up and down are different. This gives rise to different spin conductivities, right? So you can define a spin polarization of the current, taking into account this simple formula, right? Now, what happens if you pass current from this ferromagnet, where the conductivities are different, to a non-magnetic material where the conductivities are the same for spin up and down, right? Because one spin type carrier is dominant in the current, basically you end up accumulating spins. So the chemical potential for spins up and down is split in the non-magnetic material, right? Creating this spin accumulation. I can define it as the difference between chemical potential for spin up and down. And this is a non-equilibrium situation at the interface. So, and this spin accumulation will diffuse away following a diffusion equation. So essentially, this excess of a spin up will flow out of the interface and the spins down will flow into the interface to compensate. So this will be this pure spin current being created, right? So experimentally, one of the most elegant ways to observe and measure these pure spin currents due to electrical spin injection is with a non-local configuration, a lateral spin valve. So you have two ferromagnets, injector and detector, separated by a non-magnetic material, the spin channel, and you do a non-local configuration. So you pass current like that, and you measure the voltage at the detector, but the circuit is not on the same position, right? So if you only think about charges, you shouldn't measure anything. But because we have spins, we will measure something. That's what I'm going to show you. I'm going to plot here the non-local resistance, which is basically the voltage that we measure normalized to the injected current, because these are all linear response as a function of the in-plane field, the field in the easy axis of the injector and detector. If when we have this injection and spin accumulation, if the magnetization of the injector is down, then the spin current has negative polarization, right? And when it reaches the detector, if the detector is also, a negative magnetization, they are parallel, and this gives a positive voltage contrast at the interface, right? Which is what I'm showing here. If by applying the magnetic field, we switch now the injector, now the spin current has positive spin polarization because the information is taken out of the ferromagnet. Now it's an anti-parallel configuration. That's what we see here. So the voltage changes sign completely, right? The contrast now is the opposite. But if we further increase the magnetic field and the detector becomes positive again, so then it's again we have a parallel contrast and the positive voltage is measured again, right? If we sweep the magnetic field in the opposite direction, we will have some hysteresis. But this difference between parallel and antiparallel configuration, that's the indication that we have spin currents being detected at our detector, being reached there, right? So far, these kind of experiments have only been achieved using ferromagnets, of course. Now we have also the spin Hall effect is another way to create pure spin currents, right? Here you only need spin orbit coupling. So if you pass a current, due to spin-dependent scattering, you will have this separation of spins up and down. And this actually is a transverse spin current. This follows the right-hand rule, right? Spin polarization, charge current, spin current have to be orthogonal to each other in general. And the conversion efficiency is given by this parameter theta, the spin Hall angle, right? So if you have the right-hand rule in a device like this, you will also have, spin current in the vertical direction with the spin polarization pointing along X, for instance, right? You will have the two things simultaneously. And in this lateral spin valve that I told you about, we can also measure the spin Hall effect. So if the injector now is a material with spin orbit coupling, and now we do another bias configuration, we basically pass the current across the wire. Here we are not injecting the spin into the normal magnet. We just pass current through it. Due to the right-hand rule, we'll have spin current flowing out of plane with spin polarization in the X direction, right? And then once it's in the channel, it will diffuse everywhere. It will also diffuse into the detector, right? So it will fuse in this direction, and the spin will always be fixed because it's fixed by the spin Hall effect. Now, in order to detect this, our detector, which is still a ferromagnet, will need to be parallel to it. So if we saturate it in the opposite direction, this will be anti-parallel. We will have a negative voltage. And if we sweep the magnetic field, because this is the hard axis of our detector, it will basically coherently rotate. When it's 90 degrees, there will be no signal. And when it becomes parallel, it will be positive signal. So again, and then on the way back, there is no hysteresis in this case. The difference is again the spin signal caused by the pure spin current of the spin Hall effect. These experiments also have been done with non-magnetic materials and also with ferromagnets, because ferromagnets can also have a spin Hall effect. But the effect is even under time reversal, meaning that if the material is magnetic, doesn't matter if you switch the magnetization, the spin polarization will not change. Okay. So as a summary, we could say that in lateral spin valve, we can have these two types of biasing geometries to electrically inject spins or to just pass current through the material, right? If the material is not magnetic, electrical spin injection is not possible. We can only have this configuration, the spin Hall effect configuration, which is even under time reversal. If the material is ferromagnetic and we do this kind of biasing geometry, we have electrical spin injection and it's odd under time reversal, right? If we switch the magnetization of our injector, the spin current becomes, polarization positive or negative. But if in the ferromagnet we do this configuration, we are going to inject spins due to spin Hall effects. And even if we reverse the magnetization of the ferromagnet, the spin Hall effect is even under time reversal. So the spin current will not change sign. And what I want to show you today is that using a compensated magnet, we are also, even if the magnetization is zero, we are able to inject spins electrically, being odd under time reversal symmetry. And in this other configuration, we are also injecting spins which in a symmetry which is odd under time reversal. So this mechanism will be different from the spin Hall effect measure here. The two things simultaneously. And we will show that the only explanation for this will be that the material is an altermagnet. Okay, so I will go fast at this point because we've seen the previous talks by Olena, especially the differences. But if we think about electrical spin injection in ferromagnets, the spin splitting leads, as I mentioned, to a spin polarized currents, right? But in antiferromagnets, due to spin degeneracy, if you pass a current, the current is not spin polarized. But in the case of altermagnets, because of this alternating spin splitting, This means that when we pass current through it, again, the current will be spin polarized, right? And not only this, but if you can control the current direction, you could even change the sign of the spin polarization. This also means that in certain directions, for instance, if you put the electric field across the nodes of the two Fermi subbands, the spin polarized current will create a transverse pure spin current. Okay, so in certain directions, you will get the transverse pure spin current. This resembles the spin Hall effect because its spin current is also transverse, but the origin of the effect is completely different, right? It has nothing to do with spin orbit coupling. It's due to the alternating spin splitting, right? This is sometimes called the spin splitter effect. And the altermagnet I'm going to talk about is the ones we've heard in the previous two talks, manganese 5, silicon 3. So thin films grown by MBE stabilize a phase, which is proposed to be a deep wave altermagnet by the theoretical calculations. The material is a compensated magnet for sure. It has no net magnetization. We heard from Helena already this. And also we heard from Helena that this material shows anomalous Hall effect. So it's a nice way to see how the nil vector can switch. Also, Olena talk is about understanding the details of this anomalous Hall effect, right? But here, what I want to show is that how from these thin films we can pattern them to create nanoelectrodes to integrate it in the lateral spin valve, so we can try to see if indeed spin injection is possible in these materials, right? So we fabricate devices like that. And now I'm going to show the results. In any device, as a reference, we always have copper and permalloy electrodes because that's what we're going to use as a detector and as a non-magnetic channel. So just sanity check to make sure our device, our material works. We can do a standard lateral spin valve experiment with the permalloy, and we see this nice spin signal that I described before. If we do the other configuration, passing current along the permalloy only, along the injector, if we put the magnetic field in the easy axis, we don't see a signal because it's not in the right direction to detect the spin Hall effect. You need to put the magnetic field in the perpendicular direction along the hard axis of the permalloy. And if we do this, we also see the expected signal, right? So we have the two spin signal amplitudes, which in the second case is 1 order of magnitude smaller than in the first case. And that makes sense because the spin polarization of permalloy at this temperature is around 35%. These experiments are at 100 Kelvin, while the spin Hall angle is around 2%. So it's 1 order of magnitude smaller. So the signal is 1 order of magnitude smaller. If we now do the same experiments using our manganese 5 silicon 3 electrode as injector, right, with this configuration, we see a very clear spin signal again, right? So the first switching corresponds to the permalloy, it's the same value as the reference, right? But then at much higher fields than permalloy, we see a switching back into the parallel configuration. It has like some intermediate steps, but eventually they saturate, right? So there's a very clear spin signal observed. If we now do the other biasing geometry, so passing the current only along the manganese 5 silicon 3, but we still keep the magnetization, the magnetic field along the easy axis of our permalloy, what we see is basically the same effect, the same result, right? If this is a spin Hall effect, should not appear because it doesn't fulfill the right-hand rule of spin Hall effect. So this has to be something different, okay? This something different has the same amplitude as the spin injection experiment. Basically, the two signals are basically the same in amplitudes, and they seem to be odd under time reversal because once you have one switching of the permalloy, then it switches back when something in the manganese 5 silicon 3 switches back, right? In order to understand better what's going on, in the very same device where we had the electrode to inject spins, we also have a cross, so we can perform in situ anomalous Hall effect measurements, which gives us a lot of information, as we saw from Olena's talk this morning, right? And what we see is that when we do this experiment, we see very clearly a very nice anomalous Hall effect with 2 time-reversed states at 0 magnetic field. What's worth mentioning is that here the magnetic field is applied in the plane, in the easy axis of the permalloy, right? So it's not an out-of-plane measurement, but still we see these 2 states. That's, as we saw from Olena's talk, the landscape, the energy landscape is very complicated in manganese 5 silicon 3. So even by applying an in-plane field, we can make the nil vector to switch between 2 states that give rise to anomalous Hall effect. But at the same time, in the magnetization measurements that we perform before patterning the device, there is clearly no true net magnetization at 0 field, right? So the material has it's a compensated magnet, but still it has two well-defined time-reversed states. Also, it's not a single state, it goes through different intermediate states like 1, 2, and 3 before fully reversing. That's important because when in the very same device we perform this, again, the lateral spin valve experiment, we see here again the spin valve as I showed before, and you see here like the 1, 2, 3 steps, right? So the nil vector is not switching a single way, but it has some intermediate metastable states. But what's clear is that between these 2 states, the spin current that is being injected has opposite polarization, and we can confirm this by presetting our altermagnet at very high negative fields. We apply -2 Tesla, but then we go around 0, and we only sweep the field around 0, and only the permalloy is switching, right? And we see these nice contrasts with a negative signal. So here the spin polarization is negative. But if we preset our altermagnet with a positive magnetic field, now the nil vector has switched, and now we only switch the permalloy, our spin signal now is positive. So we have, see here we see the time reversal symmetry breaking of the spin current that we are creating between these 2 states. So to understand this, simultaneously what's going on, if we imagined the simple picture of the 2 spin subbands, in the case of manganese 5 silicon 3, they are not orthogonal to each other, they're not 90 degrees, but 60 degrees rotated. And in a configuration like this, if we pass current in the x direction, that's how is our spin injection biasing geometry, we are injecting a longitudinal spin current, so a spin polarized current, which is, let's say, positive, it's red right here. But if simultaneously, with this configuration, we pass a current along the wire in the second biasing geometry, right, the bias like that, we are creating, due to the spin splitter effect, also, we have a transverse component that is injected into the copper, which is also positive, right? So spin polarization is positive, is red in both cases, right? And if we do time reversal, operation, and the red becomes blue and the blue becomes red, or the nil vector is fully switching, now with these 2 configurations, we are injecting spins, longitudinal spin current here, transverse spin current here, which are now negative, right? So they were positive, they are both negative. So that's why the switchings in both configurations is very similar, because basically the effect is the same, right? And in one, you're injecting longitudinal spin current, the other one is transverse, but the amplitude should be more or less the same, right? But this is very qualitative. So in order to make it a bit more quantitative, our theoretician colleagues perform first principle calculations on this material, so they can really know the band structure. And here is the Fermi, the cut at the Fermi energy. You see the 2 subbands, the red and the blue, right? They are not simple ellipses, as I wrote before, but more or less. And from here, they can quantify the spin polarization, which is expected when the bias is applied, in this particular crystal direction, which is the one where we pattern our devices. And the spin polarization expected is around 10% in this case, okay? While if the electric field is applied in the vertical direction, a transverse spin current with a spin polarization of around 7% is expected, right? So both values are very similar, and that's why when we do the two biasing geometry measurements, the amplitudes are very similar, because basically we're having the same kind of spin polarization of our injected spins. So finally, in order to try to see if these numbers are reasonable, so if with these spin polarizations we should expect this spin signal that we obtain, we did, with the help of our colleagues here in San Sebastian, the group of Sebastian Bergeret, a one-dimensional spin diffusion equation for our device, where we have an altermagnet instead of a ferromagnet. These spin diffusion models are very common in metals and ferromagnets. So we apply it with altermagnets. The equation is something like that. It seems very complicated, but in fact, most of the parameters here are well known. We know the resistivities, the dimensions of our device. We know the spin parameters of our copper, of our permalloy, because they are from the reference values, we can extract them. We have them very well controlled. So the only things that we don't know first is the spin polarization, right? Which we have it from first principles. So if we assume it has to be of the order of 10%, which are the values we are getting, and we know that our spin signals are typically of the order of 0.3 milliohm, the only unknown parameter that we have here is actually the spin diffusion length of this altermagnet. That's the only thing we don't know. But then we can actually extract them from this equation, and the value we get is around 50 nanometers. Okay, so this is essentially one order of magnitude longer than ferromagnets. While the spin polarization of the altermagnets, around 10%, is of the same order of ferromagnets, right? So these are very interesting numbers that for potential applications will need to be taken into account. So I'm reaching the end of my talk. So these are the conclusions, right? So I hope I convince you that what I show is a direct experimental observation of an electrical spin injection in a compensated magnet, right? And that the time reversal symmetry breaking of the spin current that we obtain in these two biasing geometries can only be explained with a picture of altermagnetism, okay? We can even quantify the spin transport parameters either with first principle calculations or with our spin diffusion model of the altermagnet. So that gives us some quantification of the parameters. And that's it. Let me finally go to the acknowledgement. So this is our group at Nanogune, but I would like to highlight the role of Jone. She's the main author of the results I've been showing today. But this is, of course, a very large collaboration, especially with Prague, with Helena Reichlova. It's been a back-to-back, hand-to-hand work that I'm showing here. And we had strong support by Lisa Miches that provided these manganese 5 silicon 3 samples, and a lot of theory support from Olena, from Libor, from Sebastian. Funding, I never forget this. And thank you for your attention.
Okay, do we have any questions? Okay, then I'll ask a question. So you had this figure where you had the electric field parallel to the nodal line.
Yes,
So I was just wondering if you could explain a bit more about why that gives a transverse spin current, because in some way I would have expected that to be like an antiferromagnet.
Yes, you mean this, right?
Yeah.
Yeah, that's in the ideal case. Well, that's simply, because of the a spin-dependent conductivity. When you pass the current in this direction, you have two the current. It's not parallel to the bias, so it has certain angle, and this angle is opposite for spins up and spin down, right? So if you just simply take the definition that the charge current is one plus the other, and the spin current is one minus the other, what you will see is that the charge current, of course, will be it will be parallel to the bias, to the electric field, right? So you have a charge current will be, I don't know if you see, sorry, the pointer, right? So the charge current will be around here, but the spin current is the difference between the two. So the vector will go from here to here, right? So in this
so it's like a component of it that's like up and down going in opposite directions.
Yes.
Yeah.
Yes, and this is exactly happening at the nodes, right? So in the other case, for instance, here, all the spin current is parallel to the charge current, so that's why it's a spin polarized current. You don't have any transverse component, right? And here is a purely transverse, but anywhere in between, you have contribution of both, which is actually what's happening in our manganese 5 silicon 3. We measure with the two configurations, and the second biasing configuration only injects the transverse spin component. It's not purely spin. It also will have some longitudinal component, but the one we inject is a transverse one, and it's not zero.
Okay, I see. Thank you. Then I think we thank the speaker again and move on to the next one.
Yeah, I'm trying to share this. If I can.
Yeah, so our next speaker is Juan Jose Palacios. So please go ahead.
Yeah, thank you. It's a pleasure to participate in this workshop. Maybe next time I will be able to meet you guys in person. So yeah, today I want to talk about the how you can actually build all kind of magnetic phases on graphene just using hydrogen atoms. The only thing you have to do, quote only, quote, is to place them with atomic precision wherever you like. So first of all, yeah, I'm speaking from Madrid, Spain. So if you ever have a chance to come here, just drop by, and I will be happy to host you. As an introduction, just one slide of the things that I do. I'm a theorist, and I like to study the linear and the nonlinear response of materials using first principles calculations. These are just a couple of examples. If I talk about the AC response, I like to study things like the Ball photovoltaic effect, the spin Ball photovoltaic effect. And if I talk about the DC response, I study things like the kinetic magnetoelectric effect, CC effect, the spin Hall effect, as we have heard, and things like that. So basically, you could say maybe these are phenomena that are related with unconventional magnetism, because this is magnetism that is induced by light or is induced by a DC current. But today I want to talk about this kind of side project concerning this magnetic graphene. And maybe at the end of the talk, if I have time, I will come back to this issue of how to study the response of magnetic materials in a maybe non-orthodox way. So these are my guys. All the work has been done by this former student of mine, Tony Garcia, now in Germany, my current student, Simran Chauresia, and my postdoc, Mauricio Quintela. And of course, I'm going to talk about experiments done by my colleagues at the Autónoma University, Ivan Briega. This is the head of the group, and the work has been mainly done by his student, Beatriz Viña. So maybe you are not, all of you guys are familiar with graphene and magnetic graphene, so I'm going to go back to the basics very quickly. So like I said, back to 1950. So back then, Longet-Higgins tell us something like that. He told us the number of ampere electrons present in the ground state is at least as great as the number of carbon atoms having deficiency of valence bonds in any principal resonant structure. So if you're not a chemist, there is no way you can understand any of this, okay? But fortunately, a few years later, Lviv translated into physics jargon, and he told us essentially the same. For the Hubbard model, in the repulsive case, and if you have a bipartite lattice, half filled, then the ground state, the spin of the ground state is 1/2 the difference in the number of sides in each sublattice. We tested that a long time ago already for nanographene, and we saw that if you have a nanographene that has some sublattice imbalance, like this one here on the left, then you have a ferromagnetic system, nice ferromagnetic graphene. People are studying these guys nowadays a lot. But if you have a nanographene that is where it is balanced in terms of the lattice sites, same sites for both lattices, then the total spin is 0, of course, but you can have a local magnetism on the edges. So Lip's theorem holds both locally and globally. This is what my guys, my colleagues tried to test some time ago. They created holes on graphene, and by STM they wanted to see if actually there was some magnetic moment appearing in this case. Actually, a magnetic moment of 1/2 only, because there is only one atom removed. They saw a peak STM. They saw at the Fermi level. They didn't see any traces of spins or ampere spins, ampere electrons. And the reason was that when you create a hole in graphene, then this hole reconstructs, and this invalidates the Lip's theorem, unless you can manage somehow to avoid this reconstruction. But then it was the idea that, of course, if you add hydrogen on graphene, this hydrogen atom binds covalently to the pz orbital of one of the carbon atoms, and then this pz orbital is effectively removed from the graphene, from the pi cloud. And then this actually creates a nice hole, preserving the symmetry of the lattice and preserving Lip's theorem. And yeah, this gives definitely a nice cloud of spin 1/2 around the hydrogen or around the atom where the hydrogen was deposited. We typically do calculations, DFT calculations with periodic systems. So when you look at it, what you look at is the bands of the system, and you can see how one band, spin up band, is fully occupied, and the spin down band is fully empty. So good, so far so good. And happily for the experimentalists, this also holds for graphite, which is important for them. So they tested it. They went with STM, and they now look at the density of states, or the DIDP curve here, and they saw this spin splitting, which you would expect for an ampere spin at the mean field level. And this interaction, or the U-term, the Hubbard term, if you want, has to do with extension. It's a small number and has to do with extension of the localized state or quasi-localized state that is created when you create this hole. So everything was great. The theory was fine because we could test everything, and we saw that the same essentially results as experimentally. This is an indirect measurement of the spin, of course. This is not a magnetic STM. But you can try things like you can dope the sample, and if you dope it, you can eliminate this spin splitting, because you are either fully occupying the localized state or just getting it empty. So everything checks. So it was great. So when you have two hydrogen atoms now, if you follow Lip's theorem, what you could expect if you place them on the same sublattice, these two guys should couple ferromagnetically to have a spin 1. And yeah, this is what actually happens. So these are just a couple of examples. You just place them on the same sublattice, and then you have this nice ferromagnetic coupling, weak but ferromagnetic. And when you place them on opposite sublattices, then yeah, following Lip's theorem, you have a spin 0. And if they're sufficiently far apart, you still maintain this local magnetization opposite in spin, local magnetization around these hydrogen atoms. Only when they get closer, this magnetization is killed completely, entirely, quenched, if you want. So experimentally, this was tested. Again, a dimer shows these nice peaks at the Fermi level spin split. AB dimer doesn't actually show anything at all, because you have totally killed the magnetization. Again, this is an indirect measurement, but you have to believe me. And even if you have two guys that are sufficiently far apart, or at least decently far apart, still this magnetization is gone. So you have to keep them apart at a relatively long distance if you want to maintain this antiferromagnetic coupling and the local magnetic moments that are induced in this on graphene. So good. So 1 year ago we knew that if you don't have any magnetism, if you don't have any hydrogen atom, the system is diamagnetic, of course. If you have one or isolated atoms, you have paramagnetism. If you have two guys close enough, then they couple ferromagnetically, good. If these two guys are sitting on opposite sublattices, they couple antiferromagnetically, great. And if you have more than two, for instance, three, then you have a ferrimagnetic system. This antiferromagnetism is kind of a trivial because you only have two guys and it's not particularly exciting. The idea was to build larger systems. And what you do is you just come with your tip and then you apply a bias voltage, and then it happens that the tip is platinum and you have hydrogen in the atmosphere or something. Then you can deposit relatively close to each other a bunch of hydrogen atoms. And then what you do, in this particular case, for instance, half of them are up and half of them are down. And what my colleagues do is they go with the tip and they can actually pick atom by atom the ones they want. And in the end, you can end up with something like this. This is a totally ferromagnetic system. All the spins are pointing in the same direction. Again, you cannot see that explicitly, but we know it from theory. But all these guys are sitting on the same sublattice. So this is exactly what you in this case, what they wanted. But now, as I said, we wanted to build more sophisticated structures. And then we decided, how can we build an antiferromagnet? I mean, a little bit more sophisticated in the sense that more than two guys, of course, and out of this, with this procedure. What you have to do is you do the same. You just deposit a bunch of atoms somewhere on the sample, on the surface of graphite in this case, and then you, hopefully or luckily, you realize that you find 4 of them here that actually satisfy what you would expect for a traditional antiferromagnet. It satisfies PT symmetry. So what you do is you remove the rest of them with the tip trick, and then you end up with your 4 hydrogen atom antiferromagnet, like I said, satisfying in this case PT symmetry. You can call it P parity or inversion, or you can call it C2 because we're in 2 dimensions. So either way. And then when you compute these bands, then we consider a crystal of these systems. Of course, experimentally they only have 1 cluster, but in theory we repeat it with supercells. Then we get these DFT bands that are, as expected, fully degenerate across the whole Brillouin zone. This is a Kramer's degeneracy. I know that you guys, well, this is very robust. You can do it with a Hubbard model, you can do it with DFT, several configurations. This is, of course, always the case. I know you guys are probably very familiar with the group theory jargon and symmetry considerations. Let me just go maybe quickly just to set up the language, and in case some of you don't know it. So basically what we have is a Hamiltonian where you have a non-magnetic H0 term and a magnetic part defined by some spin configuration or some magnetization or vector field, whatever you want to call it. And this non-magnetic Hamiltonian actually is invariant under symmetry transformation. These transformations are usually denoted by this. You have a transformation that acts on the spin space, and then you have another transformation that acts on the coordinates space. R would be a proper on improper rotation, and the rotation that acts on the spin must be associated with R. Actually has to be the proper rotation of R if spin orbit coupling is present. That's the only way to conserve to make it invariant. And you have translation, of course, in the spatial part. So if you transform the magnetic term now with this operation, what you have to do is you have to, of course, transform the argument of this vector field following the spatial part transformation, and then at the same time rotate with the rotation matrix the magnetic vector, the vector. And if this is invariant, then, well, you have to satisfy this condition here. So the magnetization must remain invariant under that. This is gonna be probably not the case, because if you have a system with some symmetries and then you add the magnetization, then the symmetry of the group is gonna be lower, most likely. In particular, if you add time reversal, then and the system is magnetic, then this magnetization is not going to be invariant under time reversal. But the combination of time reversal and some specific operations in real space or in coordinate space can actually be a symmetry of the overall Hamiltonian. And this is what is known as magnetic groups or Sotnikov groups. And in particular, our 4-hydrogen antiferromagnet belongs belongs to the magnetic group 2' in this case. So, but we now that we don't have a spin orbit coupling, we are free. We have the possibility now of not having the same rotation on the spin part and on the coordinates part. So now these guys are decoupled or can be decoupled. And then we look for the same condition. We want the magnetization to be invariant under the symmetry operation. And if we get this, and in particular, we get this adding time reversal, then we get to the following situation, that we have generic operations in a spin space and in real space. By generic, I mean you can have proper and improper rotations, both in real space and in spin space, because of time reversal now, where these rotations, proper or improper, these rotations are actually decoupled, completely decoupled. They don't have anything, they don't need to be related in any way. And these are just two silly examples that you probably have seen many times. This would be a magnetic group, C4, C4. If you take this group and then you rotate in real space, you take 1 to 2, 2 to 3, 3 to 4, keeping the magnetization direction, and then you operate with C4 on the magnetization arrow, and then you recover the same system. For the spin group, you will have something like that. You just use C4 to bring this guy 1 to 2, 2 to 3, 3 to 4, keeping the direction of the arrow fixed, and then you rotate by C2 now in a spin space, and then you get to get the same thing. So just two silly examples of this of these two cases. Maybe quickly, we want to understand, or we want to be able to use the jargon of spin groups. This goes back to Lviv and Penchowski in 1974. We know that spin groups can be written as a direct product of the spin-only group and the non-trivial spin group. The spin-only group is composed of operations that keep the spin arrangements invariant. For collinear magnets, which are the ones that I'm talking about today, these operations are parity and C2, parity being time reversal. And to form the non-trivial spin group, we need to worry only about these two possibilities. Either we have a group that is, I won't go into much details, but only considering the identity. This is for ferromagnets, or for compensated magnets, you have a spin associated group that is given by the identity and C2. And then with this, you can form the non-trivial spin group. And essentially, as probably you all know, what we have now is that half of the operations are not paired with spin inversion, and the other half are paired with spin inversion, and for compensated magnets. And this is what this is telling you here. So now, in the case that we are talking about, this antiferromagnet formed by 4 hydrogen atoms, the generating element in this case for the second subgroup is, or for the second part, is the parity. And then if you put together the spin-only group operation and the non-trivial spin group operation, and we multiply them, then we get to the condition that we all know that gives Kramer's degeneracy, because now we have parity parity in real space and parity or inversion in a spin space, and this gives rise to the known degeneracy across the whole Brillouin zone. So altermagnets, we can build altermagnets, of course. This was the whole point. And now the only thing we have to do is to find the point group that we like. In particular, now the point group that we like, is this given by identity and mirror symmetry. And the non-trivial spin group, in this case, is just simply formed by these two elements, identity and C2 in a spin space and mirror in real space. And well, I mean, it's kind of an obvious thing, but if you take a look at this arrangement here, if I perform C2 operation on a spin, changes sign, and if I perform a mirror symmetry, then I go back to the same situation. So yes, I have an operation that leaves invariant my system of 4 hydrogen atoms. You are looking at colors here indicating a spin up and a spin down. Again, I insist that we know the spin on the basis of the theory. So not direct measurements of the spin, but we know that guys sitting on one sublattice with this particular non-isotropic cloud of spin are pointing up or down, and these other ones with this non-isotropic cloud for the spin are pointing in the opposite direction. So we know it, but it's not something that you actually see it with STM, of course. And how do we know this is an altermagnet? Because we do the computation, we do the calculation of the bands, in this case for a periodic arrangement, and we see what we were expecting. So with this particular spin, non-trivial spin group, and with the whole operations, this is what we would expect. So when we apply mirror symmetry and C2, we go from kx to minus kx and flip the spin, which give us the degeneracy at the line kx equal to 0. And this is exactly what we see in this case in the Hubbard calculation. And when we perform the other operation remaining, that is, we combine this with the spin-only group operation. Sorry, I changed the notation here. And when we go from kx, sorry, from minus kx to kx, and we also invert ky, the spin goes up and down twice, and then this imposes the degeneracy in ky equal to 0, which is exactly what we see in the band. So this is the standard plot that everybody uses. So we are looking here at the spin splitting, somehow plotted. And then, yes, we have the degeneracy exactly along kx equal to 0 and ky equal to 0, and spin splitting in any other direction. So this is exactly what should happen. So that was a Hubbard-Hamiltonian mean field theory. We can do it with DFT just to make sure everything is extremely robust. We get the same. In this case, we can see here the splitting along the directions that I told you about, and the degeneracy along these symmetry protected lines where we should have degeneracy, which is from K to M in this case. So we can actually build not many things, but we can build an I-wave altermagnet with 6 hydrogen atoms. And this is the case here. Now we have this more complicated low structure, if you want, here, and everything checks. So the theory and the calculations, in this case, Hubbard calculation, everything is in place. So, well, maybe also interestingly, we cannot only form or build altermagnets, we can also build what we call leaf-free magnets. Actually, these are the simplest ones, because when you have just a bunch of atoms compensated, so same number of one sublattice and same number of the other sublattice, compensated, but with no symmetry at all, you have a leaf-free magnet. So the system is compensated, but by Leaf theorem, the spin is 0. So this is just exactly what it's so difficult to obtain or to achieve with real materials, right? It's not so easy to get a compensated ferrimagnet. You have to tune chemical potentials and things. And in this case, what happens is that now you have no symmetry protection at all anywhere, and you have a spin split bands all across the whole Brillouin zone, as you can see here in this case. And again, this is very robust. Again, different types of calculations, different systems. They all satisfy exactly is what I'm saying, regardless of whether you compute DFT or you do Hubbard-Hamiltonians, Hubbard-like Hamiltonians mean field. You get always this spin splitting across the whole Brillouin zone. So what are we working now at, particularly my colleagues, in how to measure this? And this is difficult because with STM, it's hard to distinguish antiferromagnets and altermagnets. And there is a chance maybe to distinguish them from leaf-free magnets. I'm not going to go into the details of these calculations. We are trying to understand, this would be up here, you see the experimental DIDV curve. And these are some attempts of doing DFT or tight binding Hubbard models calculations to compare with. And the reason why this is difficult is because in these experiments, you have, at the same time, you have elastic transport and inelastic transport. And these two things get compounded and make hard to understand these DIDV curves. So, well, we are working on that. Maybe next time I will be able to tell you that we can actually distinguish these different systems. But there is another possibility, there is transport. And now my colleagues are building this beautiful machine to actually do transport and STM at the same time, I mean lateral transport. There is a chance that we can actually see something in transport because both leaf-free magnets and antiferromagnets are actually stable under gating. So you can gate them and the spin configuration essentially remains as it should be, but the lead ferrimagnets acquire some final magnetization, and antiferromagnets don't get any magnetization when you dope. So this is good. Then we would be able to distinguish probably lead ferrimagnets from antiferromagnets. And yeah, that's gonna be next year if I have the chance to tell you about it. So the summary of this part, if I have, I don't know if I have more minutes here. The summary of this part would be, yeah, we were able, or my colleagues were able to build with this precise positioning of the hydrogen atoms on graphene antiferromagnets, in this case with PT symmetry, altermagnets, in this particular case with mirror symmetry paired with time reversal. This would be, using the spin group jargon, would be the group M2. And lead ferrimagnets, which do not have actually any symmetry. And in this case, the spin splitting is complete across the whole Brillouin zone. For altermagnets, as we know, the spin splitting is directional. And for antiferromagnets, there is no spin splitting. And if I have time, I don't know if how am I doing with time?
So we have like 1 minute, but you can have 3, and we can have less questions if you want to. If you have
Just
something
very
more,
quick,
you can say quickly.
very quickly. If my guys were able, if my colleagues were able to actually build ferromagnets out of this just by placing them all in this very nice arrangement, then we are very interested in actually computing excitons and magnons using the same formalism. And for that, we have been actually working hard on in machinery to compute from first principles excitons and response, including excitons, linear and nonlinear response. And we are using this machinery now to compute also magnons. And the idea is that we are solving the Bethe-Salpeter equation, but now using spin flip excitations, spin flip electron hole pairs. And without going into the details of what is it you have to do to get things right, basically with Hubbard models, where are described nicely in these ferromagnetic systems in particular, we can actually get properly the Goldstone mode. This is just the bands, the quasi-particle bands in this case for the ferromagnetic system. And this is what I want to show. With Bethe-Salpeter equation formalism, we can get the Goldstone mode right. So we can get zero energy at zero frequency at the gamma point. And at the same time, with the same formalism, we are getting the excitons. And this is nice because we want to export this formalism to real materials, if you want. And in a way that we can actually compute both magnons and excitons at the same time and be able to understand the response of, at least of semiconductors in this case, the response of semiconductors fully for the spin flip and for the spin conserving channel. That is a problem if you do unrestricted Hartree-Fock because the Goldstone mode is violated. We're working on many things to be able to carry out this, to carry this over to real materials. And yeah, I stop here, leaving you with the summary. As I said, I won't repeat myself, but this is a nice platform to study unconventional magnets. They are toy models, but we can learn a lot from them. Thank you.
Okay, do we have any questions?
Thank you for the talk. I have a question about the experimental realization. Is there, or there's evidence for magnetic correlations, but is there evidence for magnetism, or in the sense of long range or symmetry broken magnetism?
Yes, it's not part of this talk, but my colleagues are studying this inelastic tunneling spectroscopy, and they can actually correlate with theory. They can correlate these magnetic excitations. So in particular, they are doing it for systems with 3 hydrogen atoms, ferrimagnets, and they actually are beginning to understand they're correlating very nicely what they measure with what you would expect in terms of theory. It's indirect in the sense that you are measuring excitations mediated by electron hopping or electron tunneling. But it's really, I could say that it's convincing at this point.
Okay, thank you.
Okay. See any more questions? So then maybe we thank the speaker again.
Thank you, guys.
Okay, can you hear me?
Yeah, we hear you. Yeah,
Just
now we see the full screen. Yeah.
Okay.
So that's good. Yeah. Yeah, so the next speaker is Ralf Clausen, so please go ahead.
Yes, thank you very much. Sorry for the confusion. I'm presently at a different workshop in Paris, so I have to first of all to get a good working internet, which was a problem. Then I didn't have a camera that was working, and now we're finally here. Let me apologize first that I'm not there in person. I would have loved to come, but I have committed to this workshop here before I was asked to participate in yours. So that's where we are. This will be similar to what you have heard in the previous talk. This is about model or toy systems, and it will be mostly STM on surfaces and specifically on monolayer, atomic monolayer on semiconductor surfaces. And we use them as model systems for two-dimensional, almost ideal two-dimensional quantum materials. The work that I'm going to present is not the work that I have done, but it's of course the work by many collaborators, in particular the students in my group that I pick here, depicted here. I will not pick out a particular person because there was a lot of contribution from many of these students. Then there was a lot of collaboration with local and theory elsewhere, as you can see on this list. And there's also a little bit of photo emission from synchrotron, but in this talk I will mostly show you STM work. Now the point, what I want to talk about is mostly topological quantum materials. There is also other systems, I will mention this at the very last slide, on highly correlated systems, but this will be focused on quantum spin Hall insulators, which are two-dimensional systems, which, as the name implies, are insulators in their bulk, but they display metallic edge states that are running around the outer edges of the material. And they're not only metallic in the sense that they fill the band gap, but they also spin polarized and in particular spin momentum locked, as is depicted on the right panel here. I think you can see my mouse. Where the right moving branch of this edge state is, for example, spin up, whereas the left moving branch has spin down. And that has the consequence that if you have an electron sitting in the right moving part, for example, and it hits on a non-magnetic, non-time reversal breaking impurity, it cannot be scattered into the other direction because that would require a spin flip, and that's not possible as long as you preserve time reversal symmetry. And that means that if you have a current flowing in the system, it cannot be dissipated by elastic scattering, and you obtain a perfect ballistic transport. So you get per channel an ideal quantized conductance of E squared over H, or if you have a real Hall bar with a left and a right edge, you will measure a quantization of 2E squared over H. And that's what was first detected and measured by my colleague Lawrence Molenkamp here in Würzburg on mercury telluride quantum wells. Now here we'll focus on other systems. In particular, I will focus on systems that condense in a two-dimensional honeycomb lattice, because one of the first quantum spin Hall insulators that had been theoretically proposed was actually graphene. It was a famous seminal paper by Kane and Mealy, where they showed that if you include spin-orbit coupling in the description of the graphene band structure, there will be a small gap opening at the Dirac point. And if you then plot the dispersion along an edge, if you, for example, cut the honeycomb lattice of graphene into a nanoribbon, and then depict the band structure along the zigzag edge, for example, as is the case, as is done here in this lower panel, you have this opening of a gap, and in that gap you will find these two spin polarized and spin momentum locked conduction bands connecting a valence band maximum with a conduction band minimum. In principle, that should be then a good system to measure the quantum spin Hall effect or the quantized conductance. However, The challenge that you face here as an experimentalist is that the actual band gap that was predicted here is extremely small, only 24 microelectron volts. And so it is very difficult to access that, not just because of energy resolution, but also in terms of temperature, because you have to go down to extremely low temperatures to have the effect not masked by thermal excitations. So the next idea you could have is to use heavier group 4 elements that have the same basic band structure, condense them into a honeycomb lattice, but because of their high atomic number, they would have a larger band gap. And in fact, if you calculate the band gap, you find from DFT calculations that it increases as expected with the atomic number. And so are these different systems such as silicene, germanine, stannine, and so forth. Only few of them have been realized, and many of them only on metallic substrates. And that, of course, is for measurement of conductance quantization, not the ideal setting. There is germanine, recent work by Harold Zandvliet's groups in the University of Twente, which is very nice. But all the other systems have not been studied very intensively in terms of topological edge state conductance. Turns out that if you go to a neighboring column of the periodic table, there are other systems that also could, in principle, condense in a honeycomb lattice. And the system that we have been working on for quite a while now is bismuthene. Bismuthene is a layer of bismuth atoms on a silicon carbide substrate. It is actually not a freestanding layer, very different from the case of graphene, but it is covalently bound to the silicon carbide substrate. As you can see in the schematic picture here, the bismuth atoms bind to the dangling bonds of the silicon carbide surface, and then it forms this honeycomb lattice, which has a unit cell, which is 3 times as large as that of the underlying substrate. That will be important in a minute. It can be synthesized if you have a high purity, highly ordered silicon carbide surface. This is something that takes a little bit of effort, but we've been able to generate these substrate surfaces. And then if you deposit bismuth on the surface, you get relatively quickly and relatively easily these bismuthene layers on silicon carbide, long range ordered, as you can see in this SDM overview. And here's in this inset a zoom in where you see this honeycomb arrangement of the bismuth atoms. Now the band structure is can be easily calculated. You find that it's basically consisting or made of bismuth 6p orbitals, and in particular, it's the in-plane orbitals that define the valence and conduction bands, with a huge gap of, in the calculations here, almost 700 millielectron volts. As you will see in a second, the actual experimental gap is larger than that, as DFT tends to underestimate the size of band gaps. And in the bottom here, bottom panel, I show you the ARPA spectrum of such a surface, and a very characteristic feature of bismuthene, of a monolayer of bismuthene or bismuth atoms, is this characteristic Rashba splitting and valence band maximum at the K point of the hexagonal Brion zone. Any thicker bismuth layers, bilayers, trilayers will lead to a much more complicated situation at the K point, and so this is a very nice indication of that you really have synthesized a monolayer. Now, very interesting is the gap size, as I just mentioned. In the experiment, it is larger than the 700 millivolts, actually 800 to almost 900 millielectron volts. This is shown here by tunneling spectroscopy using an SDM tip, where you have here the region of the valence band. Here's the bulk conduction band, and then you have this huge 0 DI/dV region, which indicates the size of the band gap. Before I get to discuss the consequences of this band gap, or what's happening in the band gap as you go to an edge of this topological system, let's first try to understand the band structure, because one of the reasons why the gap is so large is the fact that we have a covalent binding to the substrate. here on the right, you see the band structure for calculation, for band calculation where spin orbit coupling has been switched off. It's 4 times the same band structure. The only difference between the 4 panels is the size of the symbols, which indicates the relative orbital weight of the 6s and 6px, py, pz orbitals. And what you can see here is that the pz states, the out-of-plane p orbitals, which are so relevant for the physics of graphene, are actually at much lower energy, pushed away or pulled away from the Fermi energy. So they don't play a role at the Fermi level, and that is called orbital filtering. What is left is instead the px and py orbitals at the Fermi level, which form this Dirac cone, which is still a Dirac cone as long as we have no spin-orbit coupling, and they are degenerate. And this degeneracy is important because now, as opposed to graphene, you have the possibility to use spin-orbit coupling to have an electron scattered from a px to a py state at the same atom, which leads to a very strong opening, opening of the band gap, much stronger than in graphene. In graphene, you only have the pz orbital, so there is no local intra-atomic spin-orbit coupling. Spin-orbit coupling only enters the scene at next nearest neighbor hopping, and that's why one of the reasons, besides the small atomic number of carbon, why graphene has such a small band gap. So this orbital filtering, the covalent binding to the surface, is relevant. Now, if you add the spin-orbit coupling, you get 2 effects. One of them is you open this huge band gap. This is just the atomic spin-orbit coupling, and then also you have Rashba splitting, Rashba effect, because you have, of course, an asymmetric situation. The bismuthine layer is sitting on a substrate, but vacuum above it, so that breaks the symmetry and leads to Rashba splitting, and that's the reason for this almost 400 milli-electron volt splitting of the valence band maximum. If you analyze the band structure here for topological behavior, you find that it is indeed a Z2 system with a non-trivial topological invariant. So this is a quantum spin Hall insulator, and therefore the system should display helical metallic edge states. For that, we need edges. And the natural edges that we can find here on these systems is terrace steps of the substrate. No substrate, and silicon carbide is no exception, is perfectly flat. Every now and then you see a terrace step to a higher terrace. And this is the situation that you can see here. These are 2 terrace steps separated by this single step of 5 angstroms. It's always an integer multiple of 5 angstroms that you find on such surfaces. And then you have an upper terrace with a bismuthine layer on top, this one here, or lower terrace with bismuthine on top here. And so you get these natural edges. Here you have one edge, and here you have one edge. And the alignment is such that this is just imposed by the symmetry of the substrate and the symmetry of the honeycomb lattice, that these terrace edges are armchair edges. Now, so we have an edge. So what can I do with this? Let me show this here. The spectrum that you see in the right panel, which shows this huge gap, has been measured with a tunneling tip locally far away from an edge. So this is why we can claim that this is really a bulk band gap. Now, if I move my tunneling tip closer and closer to the edge, I will see an increased spectral weight, or increase of spectral weight in the gap, as you can see here, which is relatively smooth. So it fills the entire gap. So we get a metallic situation. We see a little zero bias anomaly here, but which does not completely quench the intrinsic spectral weight in the gap. So this is an indication that indeed there are metallic edge states. They're strongly confined, as you can see in this picture on the right. The gray curve is just the topography with a step edge. Here you have the lower terrace, here you have the upper terrace. And the red curve is just the spectral weight integrated over the bulk band gap. So it is naturally 0 as you go far away from the gap. But if you then approach the band edges, you see this exponential increase or exponential decay if you go back into the volume. And if you plot this, fit this with an exponential curve, you find that the decay length is typically of the order of 4 to 5 angstroms. So this is really, this edge state is confined on atomic dimensions. Just as a note on the side, this zero bias anomaly, as it turns out, in a detailed analysis, which I do not have time to go into, is just a hallmark of electronic correlations effect in this one-dimensional entity. This is the spectral behavior of a helical Tomonaga Luttinger liquid, and it shows all the relevant signatures, for example, universal scaling with energy and temperature. But let's have a look first at the topological nature of this edge state, because, as I said before, you cannot have backscattering on non-magnetic impurities in such a situation because of the spin momentum locking. And can we see this, or can we probe this in the SDM experiment? Now, here you see a typical edge situation as we find it in the experiment. Our edges are not infinitely long. This is a topographic picture. But every now and then you have a change in direction of the edge by a multiple of 120 degrees, which is just reflecting the symmetry of the lattice. And for a spinful edge state, these distortions of the atomic order or atomic crystallinity of the edge would act as an impurity scattering potential. So what you would expect to see is that an electron that's moving along such an edge, a fraction of it will scatter back, and the backscattered and incoming wave will interfere, and you will see an interference effect, which is known as quasi-particle interference in SDM. Now, if you do this here on this situation, we find the following behavior. You see in this second panel here, the local density of states, the DI-dV curve that we measure. And here you see these curves for different energies. So as we change the tunneling bias, you can see that all these curves do not seem to change much. You see a certain periodicity here, which is not quasi-particle interference, but just the atomic corrugation. You have a crystalline nature here of the edge. But as you change the bias voltage, you do not see any additional interferences that would have to be interpreted into quasi-particle backscattering. So from this picture, we would conclude that there is no backscattering from the edge kinks, and this would then, of course, be consistent with the topological protection of such an edge state. Now, the problem is, of course, it's very difficult to claim something on the basis of the absence of another observation. So the question is, can we create a situation where we can restore backscattering and then just see how strong it really is? Maybe it is so weak that we cannot see it here against the noise. And we can indeed create such a situation. For example, this is again the situation with a single edge with my spin momentum locked edge states. But suppose we could couple a second edge very close by. We can pair these two edges and allow for electron tunneling between the edges. Then we will restore backscattering. The reason is that on the opposite edge, the relationship between spin up and spin down and left mover and right mover will be reversed, so that an electron, for example, that's moving to the right, the red one up here, which is a spin down electron, can get scattered here at this point, at this kink, tunnel to the other side, and then this is still a red spin down state, but this is now a left mover. So you have a backscattering possibility. And if you have another kink here on the other side, the electron gets scattered back and forth, and you will end up with Fabry-Perot or quantum well states, if you will. And you can mimic or simulate the situation in the tight binding calculation, which is indicated here. And what you find, and as expected, is that you get a discretization of energy levels that are possible because you have a relationship between the wavelength of the electron and the energy through the dispersion, which is linear, and in a given oscillator or backscattering potential here, you can only fit in a multiple integer of half wavelength, and this adds up in this spectrum here. Now, do we see this behavior in our situation with these piecewise straight sections. And the reason, or do we have a situation where we can create, first of all, a matching or a coupling of two opposite domain walls? And there's a very natural feature in these bismuthine layers where this occurs. This is another SDM picture of a larger area where you see these blue bismuthine planes, and then these golden lines that separate them from each other. This is basically domain boundaries between different phase domains of the bismuthine layer. As I mentioned early on, the unit cell of bismuthine is 3 times as large as that of the underlying substrate, and that means that there are 3 different phase relationships you can realize when you start growing a domain of bismuthine on the surface. Now, if you have domains with different nucleation points, which are not commensurate, what will happen is that these, for example, here the red and the blue domains, they will start growing and finally find out that they do not match to each other. So they form a domain boundary. And this is exactly what happens here. So we think of them as edges, which are coupled, so electrons can move from one side to the other, but from viewed from the bulk, they are just outer edges. So what we have then is this situation, a domain wall as 2 closely coupled edges. And because these domain walls also change their direction every now and then by 120 degrees, you have these kings as scattering centers. And then we have created a situation as was depicted in my schematic picture before. So if we then take an SDS DI-DV tunneling spectrum, we find 2 things. First of all, as opposed to the bulk spectra that we had measured before, where we have a very smooth filling of the band gap, which is here depicted again by this gray spectrum, which is just measured in the bulk, you find now a very peaky set of spectrum where you have at certain energies very spiky peaks indicating strongly in energy, discretized energy levels. And if you plot the entire LDOS map of the local density of states, you find that at this energy 1, which has this pronounced peak here in this red tunneling curve, you get this spectrum where you see still a little bit of atomic corrugation. So all these details in here come from the individual atoms. But the global maximum or the global behavior is that you have one big hump here in intensity. Now, if you go to the second energy, you see 2 such humps. If you go to the next energy, you see 3 and 4 and so forth. And that's exactly the behavior that we have been mimicking or simulating here by this tight binding model. So that tells us that if I introduce a mechanism that allows backscattering, I can see the backscattering, as you can see a quasi-particle interference and the standing waves or Fabry-Perot states in these piecewise straight sections, which we do not observe for the free edges. And the free edges, this is switched off. And that's together, these 2 observations, no backscattering for free edges, but quantization for these coupled edges is a clear indication that these are indeed topological edge states which are spin momentum locked. Let's switch gears to another system, Indinine, which is a system that also shows honeycomb physics, although you would not expect it at first sight. If you deposit indium, which is in the group 3, in the column 3 of the periodic table, on silicon carbide, you do not get a honeycomb lattice, but rather a 1-by-1 symmetry triangular lattice. But this triangular lattice is special. It does not have, as you would naively expect, a C6 symmetry, but due to the symmetry of the underlying substrate, you break inversion symmetry. This is broken by the second row of carbon atoms in the silicon carbide substrate, which are not sitting in a symmetric position. And if you, for example, here, this is the unit cell of the indinine surface. And if you go along the long diagonal of this unit cell, which is this orange curve, and you take a tunneling path, a topography signal, you see that this strong asymmetry very clearly. And this will be very important when you try to understand the band structure of this material. This is a tight binding model of the band structure. This is what you see at the moment is the band structure as you would expect it for a freestanding arrangement of indium atoms in a triangular lattice. And you have 3 bands according to the px, py, and pz orbitals. The blue ones are the in-plane orbitals. The red one is the pz orbital. Now, if you put this on and this is what you see at the K point, you have clearly a Dirac point, but there are not just the Dirac point here at the Fermi level, but there are a number of further Fermi vectors where this band crosses the Fermi level, indicating that this is a metal. Now, if you introduce a substrate, you break the mirror symmetry horizontally, vertically to the surface, and that leads to a strong intermixing of the in-plane and out-of-plane orbitals, and that opens huge gaps almost everywhere, except at the K point, where you still have this remaining K point. Now, if we now add this inversion symmetry breaking from the substrate, this is the first time you can actually open a gap also at the K point. And it's very important to notice that the actual orbital composition that you have at the valence band maximum and the conduction band minimum is not just px and py, but rather the combinations of px plus minus ipy. These are just orbital angular momentum eigenstates of the z component of the orbital angular momentum operator. And so you can identify clear quantum numbers here, Lz equals -1 at the valence band maximum and Lz equals +1 at the conduction band minimum. Now, these states are actually doubly degenerate. And if I now switch on additionally spin-orbit coupling, you can actually break this degeneracy. And what you can also see as I increase the strength of the spin-orbit coupling, which I call lambda SOC here, relative to the strength of this inversion symmetry breaking, you can see that for not too strong spin-orbit coupling, I start not only breaking this degeneracy, but also to close the gap slightly. So if I keep increasing the spin-orbit coupling, the gap will close and reopen again, but now with a reversed order of the orbital angular momentum eigenstates. And that indeed leads to an inverted band gap. And I have now an insulator, which is topologically non-trivial. So I have 2 situations here. Either I have strong spin inversion symmetry breaking as relative to spin-orbit coupling. Then I have an insulator of this kind here in this phase diagram, but it's a trivial insulator. Or I have stronger spin-orbit coupling, then I end up with this situation with a different sequence of the orbital angular momentum states at the K point, at the former Dirac point. Now the question is, which situation do we actually have? Now, if you take an upper spectrum, you find an extremely good agreement between DFT calculations and the actual ARPAS experiment. You also find a small 100 millielectron volt gap at the K point, but I cannot from this data set alone decide whether this is a trivial gap or a topological gap. However, that I can do by measuring the circular dichroism, because the orbital angular momentum, which happens to be proportional to the local Berry curvature, can be directly probed by circular dichroism, where you excite your photo emission spectrum with left or right circular oriented polarized light. And then you measure the difference of the 2 intensities with respect to the sum of both intensities, and that gives you information about this, about the actual state, if you have the trivial or the quantum spin Hall insulator. Now, in the quantum spin Hall insulator, I would expect to see alternating orbital angular momentum states at the K prime and the K point, whereas in the trivial state, at the K prime point, both states should have the same orbital angular momentum, and at K, the opposite same momentum. Now, in the experiment, and this is encoded here in red and blue, at the K prime point, I see an alternating sequence red and blue, and not blue and blue or red and red. If I go to the K point, I have the reverse behavior as you would expect it from this schematic picture here. Now, for the photo emission experts among you, you may know that measuring circular dichroism in ARPAS is a highly non-trivial business, because you can also get signal which is purely relating to the experimental geometry, and you have to make sure that this is not an artifact from your geometry. So a simple way to test this here in our case is to just rotate our sample by 60 degrees about the surface normal. That would exchange the position of the K and the K prime point, and this is what done here. And lo and behold, you find indeed that if you do this, now you have the reversed polarity, or the reversed circular dichroism here at the K point, which is a clear signal that this is really intrinsic circular dichroism and gives us information about the orbital angular momenta of the valence band states at the maxima, and it clearly identifies this material as a quantum spin Hall insulator. This also has a bearing on the charge localization in this case, because the eigenstates, as I said, are p plus p minus states, which are sitting at the atoms. This is just the L equals 1 or M equals 1 spherical harmonics. And so the main point is, as you go around the atom, the phase of the wave function changes as e to the plus or minus I phi. This is encoded in this picture here. These are these donuts where you, as you go around each nucleus or each atom, you have a change of the phase here in color. However, as you go to different lattice points, you add up also an additional Bloch phase. And if you do so, this would rotate some of these donuts here, not the one at the origin of the lattice. And if you then look at the phase distribution and you put yourself here, for example, in the right half of the unit cell, you can see that if all three neighboring atoms are showing, or wave functions are looking at me with the same identical phase. So if I add them up coherently, that would give a finite signal. Whereas if I place myself in the center of the left half A, I find that the phases of the atoms looking at me are all off by 120 degrees, or 2 pi over 3. And so if you try to add them up coherently, you would get a 0. So if you then calculate the charge distribution, you find that it is not sitting at the atom, it's actually sitting between three atoms, but depending on which of the states you have been looking at, it's on the right or on the left half. So the charge not sitting at the atoms is known as atomic obstruction, and this is actually what is happening here in the system. On the right, you see again our principal situation. This is the lattice, and depending on which of the two states at the valence band maximum, for example, I'm looking at which energy I pick, my charge will be localized at the blue or the red positions, which correspond to the A and the B halves of the unit cell. Or if I add up the charge distribution from over the entire valence band up to the maximum of the valence band, I would get this charge distribution here in my lattice, which looks like a honeycomb lattice, except that the vertices of this honeycomb lattice are not identical with the atomic positions. The atoms are actually sitting here at the holes. The entire charge is sitting between the atoms and not at the atoms. So that's real space obstruction at play here in this material, and which is another indication of topological nature. This system also has edge states. I will not go into any details here. Here you can see a situation where we have an indium layer on the surface, and here's some area of hydrogen passivated silicon carbide substrate, which is not covered with indium. So this is clearly an edge here, and this is the topography. And if I look at the local density of states, the DI/dV at zero bias, I indeed find that there is a metallic edge state sitting exactly at the edge. And I can also measure the spectra here and also the confinement away from this edge. And it is very similar to the bismuthine case, confined really on atomic length scales here of almost 4 angstroms away from the edge. So I'm almost at the end. Just want to include one current thing that we're looking at. namely antimony.
You're
Antimony-
already a little over time, Ralph, so just
okay, I will go
again,
very quickly.
very
So I
quick,
just want to mention, so if you use antimony, which is also group 5, like bismuthine, you do not end up with a honeycomb, which was something that we were hoping for, but instead we got a honeycomb, a Cargomere lattice, which is quite interesting because that's most Cargomere systems that people look at the moment are first of all 3-dimensional and then mostly based on 3D metals where you have a high degree of orbital degrees of freedom and complexity. Here, this is a much simpler system. It's a breathing Cargomere where you have where the two types of triangles that you have in the lattice have different lattice constants or different hoppings between them. That opens a gap here at the position at the former Dirac point. But if you take into account that you have p orbitals here, in our case, it's just the px and the py orbital, so it's the minimum model for a multi-orbital Cargomere system, but ideally 2-dimensional. You get this type of band structure. This is the DFT level. This is the tight binding level, excuse me. And this is what you actually see in the DFT. So it's actually what you would expect to see. And indeed, we do see this in ARPAS. The ARPAS signal is not quite as intense as in the other systems that I've been showing, but the reason is that only a certain fraction of the surface really condenses in this very nice antimony 2x2. It's labeled here, that's the Cargomere region, whereas other regions are disordered and they do not contribute to ARPAS dispersion. So what I wanted to say here, this is a nice thing, a nice model system to study two things, and that's what we're currently doing. One is to check for higher order topological order in this system. This has been a very controversial debate in the literature whether or not this is really a Houthi and if it has protected corner states. This is something that we look at with SDM at the moment. And the other question is that about atomic obstruction, because the breathing Cargomere is known as an obstructed lattice for a situation where you have 2/3 or 1/3 filled band. In our situation where we have two orbitals, it is rather complex, and it turns out from the tight binding analysis that our theory colleagues have done is that each of the two bands type of p orbitals that you look at is obstructed for themselves. But if you try to vannerize the entire occupied band structure, you end up with a non-obstructed situation. So meaning that the sum of two obstructed bands does not also lead to obstruction, but also can lead to non-obstructed situation. This is again something that we would like to probe with SDM. There have recently been some very nice papers on atomic obstruction and TMDCs, and we want to transfer the idea to here. And that brings me to the end. I just wanted to introduce here atomic monolayer as 2-dimensional, if you will, designer quantum materials. I've shown you examples of topological insulators, and in particular edge state spectroscopy. But there is much more. There is also Mott insulators and possibly topological superconductors. There have recently been reports on tin on silicon 111. If you dope it, you end up with a doped Mott insulator on a triangular lattice, and there have been superconducting signals being probed, and there have been claims that this is indeed chiral. And we are trying to realize this now on silicon carbide. And finally, this is all in situ work under ultra high vacuum, but it would be great if one could also do transport experiments on these materials. For that, you need to passivate these 2-dimensional atomic layers in such a way that you do not disturb the electronic structure and at the same time can prevent them from oxidation. We succeeded in that by graphene intercalation. So chemically, that's possible to put something with a van der Waals layer on top. But graphene is, of course, in terms of transport experiments, not ideal because it's conducting itself. And so the next step is to use boron nitride as capping layer and to build real topological devices of such systems. Yeah, sorry for taking so much time. I'm happy to take your questions.
Thanks for a nice talk. Do we have any questions? Yeah.
Harold Sergeyski, thank you. Very nice, beautiful data as always. Question: with your expertise,
Do you do the twisted monolayers too, or are you going to do?
No, this is a different technology because then you need all this twisting devices, transfer microscopes, and so forth. The systems that we've been looking at were all grown by deposition on macroscopic substrates. This has the advantage of being scalable, which is for the twisted layers at the moment not really a choice. But we are thinking about applying transfer microscope techniques to the boron nitride capping. And if we can do this, we can, in principle, also think about putting, for example, monolayers or a few monolayers of niobium diselenide as a superconductor on top of one of our topological insulators. That, of course, could be quite interesting.
Thank you. There was a question. Thank you.
Thank you very much for your talk. In fact, I've read a couple of papers you mentioned here. And so my question would be rather experimental. I was wondering, in the preparation of the substrate, what is the role of hydrogen passivation of the silicon carbide? And why is it necessary, and what would happen if you don't do it?
Well, if you do not passivate it with hydrogen, silicon carbide's natural surface configuration is a root by root 3 reconstruction, which absorbs or which satisfies the dangling bonds. Once you do that, you have these dangling bonds not available for reaction with the deposited material on top. So what we do is we first passivate the surface with the hydrogen. So it is, first of all, it is passivated. So all the dangling bonds each dangling bond has one hydrogen atom attached to it. And the whole trick during the deposition is to find a temperature protocol where you at the same time release the hydrogen atoms and then bind the deposited atom to it before the silicon carbide has a chance to reconstruct into this other reconstruction. That's basically the role of the hydrogen.
Thank you. Thank you very much.
Any question from Sura? There's one more question here.
Alexander, thank you for the wonderful talk. I have question, but just because it is many new results just for me. But let's say one question concerning bismuth. This the age. So when you show in topographic image, in topographic profile, the peak, first I expected that it is just due to backscattering in backscattering standing wave, but you say it is not but I missed your explanation. Why is this peak in topographic profile? What is the origin of this peak then, if it's not backscattering?
What peak are you referring to?
Which you have shown the step on bismuth, so H of you show this topographic image with a peak on the side.
Let me see if I can go back to this. You meant
this one, for example, on the gray plot, the previous slide.
The previous, which one?
Slide, which you go through. Oh, this one. This is gray plot. This is gray curve, and this is peak on the side of bismuth. Right?
Oh, that's the gray curve. The peak on the gray curve.
Yeah, peak on the gray curve.
That could be just if you look at the left hand side, you see this white mountain range here. This could be just some adsorbed atoms or some debris or some individual silicon or bismuth atoms. Let me call this just dirt rubbish, which is sitting there.
But it can be a signature of the backscatter.
It cannot. It does not backscatter. I mean, it cannot backscatter because the electrons cannot be scattered back. I mean, whatever impurity you put there, as long as they are non-magnetic, as long as they cannot lead to a spin flip, you cannot backscatter whatever you have there. That's a nice thing. Your edge does not have to be perfect.
Okay, thank you.
Yeah, so do we have any questions on Zoom this time? It doesn't seem like that. So we thank Ralph again.
Thank you very much. Thanks for having me.
And then we thank all the speakers of this session and everyone on Zoom. And then I think it's poster session, right? You want to say